And then he did masters and PhD from IIT Delhi. He is very active researcher. His research interests include corrosion of river in concrete, corrosion of river in concrete, high performance concrete, microstructural modeling of concrete, chloride ingress, service-life predictions, and there are many more topics. He is a nominated member of Academic Advisory Board of Engineering Science at TERI, Governing Council of Dr. Fixit Institute, and Research Council of CBRI. He is the editorial board member of Magazine of Concrete Research, technical journal published by Thomas Telford, UK, and International Journal of 3 Years Dr. Fixit Laboratory for Repair and Rehabilitation in India. He is a life member of Indian Concrete Institute, Indian Society of Construction Material and Structures, Indian Society of Technical Education, and American Society of Civil Engineering, Indian section, and Masters chapter of American Concrete Institute. He is authorized various journal and international conferences such as ACE, Journal of Material and Civil Engineering, Cement and Concrete Research. Besides your various journal conference paper, he is to give lecture and publish various in workshops and conference proceedings. He has handled various consultation projects, that is more than 200 consultation research project, and Dr. Bhattacharjee supervised more than 120 MTechs and more than 10 PhD scholars. I welcome Professor Bhattacharjee to give his talk. Today he will give a talk on mathematical generalization of material design of cement-based systems. So please, you start your talk.
Okay.
Yeah.
Okay, then just a minute. Join.
Yes.
Yes, and yeah, share screen.
No, say initially it was shared, but now you have canceled.
Now it's shared.
Again.
Share content.
No,
is
now
there.
Now
It's
it
not
is
there.
cancelled. Again, you have to. No, sir, you have to share again.
Yeah, I'll do it. I'll do it.
Okay.
Right. Yes, is there?
It will come, sir. It will come. Yes, it is coming, sir. Yes, you can see.
So, good afternoon, everybody.
Yes, sir. Good afternoon.
Generally it is thought that material is all empirical. You mix something, produce something, break something, and that's it. So I just been trying to get away from that notion that it is not exactly that. You can do a lot more things there. So that's the whole idea, and that's why I've given this title. But although there is a lot of problem here. Anyway, I just want to start with this since this 100 years of Abraham's water cement ratio law, and this is the third time I'm speaking of the same thing in terms of this, because first was I think some ICI talk in Nagpur or some such place. I said that it is the Duff Abraham. This one, Design of Concrete Mixture, was published in 1920. Now it is 2020, 100 years. And he's a father of concrete science. Concrete has been there as a material, but concrete science, perhaps it could be said that he's the father of concrete science, because he started looking at it from scientific point of view, like, soil mechanics, Tarjagi. Although soil was there, people were building foundations, but then mechanics came, he adopted mechanics to soil. So he did a lot of things, concrete mixtures, and several things. I am not going to all that, but would like to pay tribute to this man who started all those. His major contributions are this. Some of you might be knowing, the figure comes a little bit later, and this is finesse modulus, a concept which is actually, I'm not showing that algebra this time, but this is there in my NPTEL lecture anyway. Finesse modulus is algebra behind this. What is the idea? It's the average sieve number. That algebra comes from his work. The concept slump cone, even today we use it very much. That's is his invention, and many others, of course. But I don't think I'll go too much into it. This is, of course, the most important. He found that strength, as measured on samples of uh, cement paste or cement-based material. In fact, particularly cement paste is what he looked into as a function of water-cement ratio in terms of volumetric measurement. But whatever it is, he found that's what he found. That's what is found. And if I write it slightly in an algebraic way, it works out to be some constant to the power another constant to the power water cement ratio. One can easily write this as a logarithmic law and all that, but I'm not interested at the moment. And this he did for OPC binder, right? So that's him. He also did a great job in terms of finding a page strength of 276 MPa by using a water cement ratio 0.08, applied pressure, and today our reactive powder concrete is based on this concept. So it's the same law again, drawn in a slightly different manner. Paste, mortar, concrete, everything follows this. So anyway, coming back to, I must introduce a little bit concrete. This is how concrete a core looks like, right? And we know that these are aggregation of inert solids, so call them aggregate. And then these are the some smaller ones would be there, but in between them would be cement sand, what we call mortar. In normal concrete, of course, this forms a skeleton matrix, 60 to 75% by volume, and paste will be 25 to 40%, 1-2% would be voids in those normal concrete. And you know, this aggregation of material, which are natural system essentially, so they are inert because you pick them up from nature, they have not been reacting, they have done or finished all their reaction potential, and that's what it is. So ingredients of concrete, if I look at it today, well, it so happened that chemical admixtures came first, water, hydraulic binder we are looking at, mineral admixtures, some cement binder, and rest all are aggregate. So that's the ingredients of concrete as we understand. But today's concrete, earlier perhaps those two admixtures were not there. Today, of course, you have at least 6 component concrete, not 3 or 4. I mean, not 4 component. But we must understand
the
that
voice, we're not getting the voice.
Can you hear me? Am I audible or is there a problem?
Yes, now it's fine, sir.
Okay.
Yes,
so,
yes,
So you can
yes,
start from this
audible.
slide.
Okay. So concrete is a particulate system. Particles, they are bonded together, right? They are bonded together. In fresh state, wet paste and aggregate system forms the concrete. So it's in a, like in the fresh states, when it is fresh, wet paste and aggregate system forms the concrete, and largest coarse aggregate particles are packed together with their interstitial voids. Not very complicated, it's a simple system. And these voids are then filled with smaller coarse aggregate, and remaining interstitial voids are filled with fine aggregate. That's at the fresh state you can think of. And the further voids within the sand is then filled by what we call paste, which is nothing but cement or cementitious, let me call it cementitious, plus water. If it is a hydraulic binder, if it is a polymer or other binder, let us say that would be, the monomer plus, which is glue, essentially, plus hardener, epoxy concrete, for example, etc., etc. So you have all this system which forms paste, depending upon, but we are not talking of this concrete is too costly concrete. So we are talking of binders of this kind most of the time, cement-based system, inorganic cement-based system. That cement-based particulate, some of them may be even inert, very fine particles, for example, if I had a limestone powder in OPC cement, normally they would not be acting too much as a reactive material, but in some cases they do. For example, some cements, limestone powder forms carboaluminate. I'm not interested in that right now. That fine part powders plus paste, so we call them sometimes as powders. Powders plus water makes the paste. So that makes the paste. Then that's what it would look like. You'll have large coarse aggregate followed by smaller coarse aggregate, and then the sand comes in, and then comes in the paste comes in between and forms the concrete. So that's what it is. Paste will come in between and form the concrete. So that's what it is. You can think in terms of another schematic diagram: large particles, smaller particles, still smaller particles, and then these are the still smaller particles, and paste are this particular one represents the paste part. So that's the material. That's the cement-based material actually, right? So cement-based materials, the particulate system bonded together. So this is the aggregate, larger ones, fine aggregate. This is the coarse aggregate, and this is the yellow one is a paste, initially plastic, then it solidifies. Initially cement paste, cement or powder plus water will be in a paste plastic form, which can deform just at simplest of the load, or in its own can move, then it is fluid, and then it solidifies, and that's how it bonds it. It solidifies and bonds it, solidifies and bonds the whole thing. Any concrete system will be like that, right? So that's what it looks like. Coarse aggregate and smaller coarse aggregate, and then after hardening, after solidifying and strength gain is hardening, this mortar is somewhere in between. So that's the concrete. Now if you look at modern concrete composites, so that's an introduction of the concrete. Now we have started, it came from 1930s, as I was saying, and then historically till 1950 not much of a development. 50 people started looking into some of the science like TC power, etc., added a lot more things into the concrete science. Then the other materials, they wanted to reduce the cost, so started adding materials, waste material like fly ash, which was also doing a good job in terms of environmental issues. That's 70s. And they also realized by 1960s or so that concrete is, after all, can degrade depending upon the atmosphere, because construction started in tropical countries, in marine environment, and that's what they realized. So those were the development in terms of how to make it concrete, which capable of withstanding freeze-thaw resistance, reinforcement, corrosion, etc., etc., etc. 80s came new development in concrete, thanks to, in fact, silicon technology. I'll not talk about that today, but it was actually silicon technology which gave us semiconductor, which gave us microsilica, and the chemistry, the polymer science, they gave us what we call hyperplasticizers, and concrete technology had an exponential change, and today we have varieties of concrete. So you have first normal strength concrete, what we understand. Then you can have high strength or high performance concrete, which till 1970s the strength was only up to 60 MPa. At best you could get up to 50 MPa or 60, not more than that. Then you started getting higher strength, so we call it high strength concrete, 80s onwards, and then high performance concrete, ultra high strength concrete, reactive powder concrete. There are several of them. Fiber were put in, that has been done quite often because that's a tradition even with mud. So for crack arrestation property, what we call also for pseudo ductility. So you see the concrete system is not simply concrete today. There are other materials, very strong material like densified with small particles. I'm not going to discuss them. Macro defect free matrix, reactive powder concrete, which can go up to 800 MPa strength. 200 grade is what has been used in structures, also bridges, and polymer concrete like epoxy or uh, polyester, and what you call methyl methacrylate. These are instead of cement and water, they have used this concrete. Some cases they have used polymer plus cement together, rubber latex plus cement, what we call polymer modified concrete or polymer cement concrete. Then these are the ones, high volume fly ash concrete or geopolymer. They started using fly ash in a great way, so that environmental concerns are reduced and the waste material is being used. Roller compacted concrete, and thus we have n number of concrete, and new binders are now coming, which I have not actually included here. New binders, composite cements, composite cement, composite cement, composite cement, cements, or Portland pozzolana cement. Some of you must be familiar. Portland slag cement, you'll be very familiar with this, because Rourkela steel plant, Portland slag cement is very much available in the eastern zone. Portland pozzolana is from fly ash, and when you mix them up judiciously, you call it as a composite cement of slag, fly ash. You can have lime-based cements like LC3. You can have magnesia-based cement. So there are a lot of binders now. And I'm not interested in telling you about the binders today, because I'm talking of something else. So you can see the concrete system. It's a composite, and you can have different binders. And you have a skeleton matrix, which is formed by the aggregate system. You can put fiber reinforcement and composite cement and binders. You can have, as I'm saying, different varieties. So for example, if I may, skeleton matrix is a fiber reinforcement, and if you see, you have O stands for OPC, so this is OPC. P stands for a plasticizer, which will be very much there. W is for water. S stands for, must be for silica fume or something, OPW. So you can have varieties of binders. So OPC, pozzolana, some pozzolana, water, and plasticizer, water, and some silica fume or something like that. And then high performance concrete you want to get, you use quartz as aggregate. So this is what it is. And then vertically, if you go up, use steel fiber or some fiber, then you can get high performance concrete. So you can have combinations of binders, combinations of matrices, recycled aggregate, varieties of aggregate system you can have. And you can have different types of fiber reinforcement like steel, polypropylene, polyester. All this could be there, and therefore you have actually varieties of materials possible, so which is actually a composite of cement-based composites. That's what we'd like to call it, cement-based composites. So cement-based system, we can like to call it. They are not the ordinary concrete alone, there are many more. But ordinary normal strength concrete also belongs to this general class of materials. So, and this can have quite a bit of good performance. So anyway, I'll just mention this maybe sometime. What are the performance desired for structures? Safety against mechanical load for structures. Long-term performance in service, creep, shrinkage. You need some performance related to that. Particularly in tall buildings or long span bridges, they will become very important, because there can be differential kind of a deformation occurring. Some are high shrinkage, some are less, drying more. In multi-story building, above 33-story building, this becomes important issues. Then of course, durability, performance, I'll define this sometime, and it's quantified in terms of service life of elements. So these are for structures. Structural engineers will demand this, and any structure nowadays will actually demand sustainability. Although I'll not talk about it today, but this is what the performance will be looking about. Now, what does material do? Material's role, it should have adequate, depending upon the situation, axial, flexural, or tensile strength, and could be there. Some cases strength to weight ratio may be important. You might want in tall buildings lighter, strength to weight ratio. So you want light material, lesser weight. But some cases you might need opposite. You might need massivity, like dam, gravity dam. So this is what concrete can provide, robustness. So it can provide the stability against sliding, overturning. And that's why concrete is so versatile. It can provide this, you can even make this, and these are adequately available. Adequate stiffness is provided by modulus of elasticity of the material. So this is what a structural engineer demands from the material. Then not some case, many cases, the structural engineer would want post elastic. That means your deformation can come back. That's elasticity. If you release the stress, strain will be zero. So beyond that, after yield or whatever we call it, you want ductility. That means a lot of deformation capability, adequate warning before and through large deformation prior to failure. This is what you need, so that in a connected or jointed material, one system is actually damaged, it will show a lot of deformation and therefore it will not collapse, but short deformation will still be hold in position. So unless you have several mechanisms formed, you would have done limit state designs. Then some cases endurance limit stress after infinite number or at least 10 to the power 6 million cycles, impact toughness, abrasion resistance. So some or all of them may be demanded from the material. So we'll look into some of them. Some cases resilience and damping properties. So these are demanded from materials, from the structural designers. Now this is important. Resistance against changes with time, physical or chemical degradation under service. That is what relates to durability. See, durability is related to when the structure is exposed to atmosphere, some kind of service atmosphere, material should not change. There shouldn't be chemical degradation. It can withstand the load, but if it degrades, then it will be under considerable stress, distress, what we call it. So that's what is related to durability. And we'll look into this because here the mathematics can come in a big way and it's there already. But since this is moldable, all this material is moldable, this is important. That is that the moldable form, we should be able to mold it. So rheological properties at fresh or what we call plastic state for moldable material is important. And material design must take care of all. So you must look at its initial plastic state, rheological properties. That's what the scientific terminology for plastic material. Right, the study is the subject. The rheology is the subject of behavior of plastic material under little stress and its movement, because as we shall see, it's viscoelastic. It could be viscose, viscoelastic. So you have yield stress or some kind of yield, and beyond that, it would behave in a plastic or truly fluidic manner, as we shall see later. So this we must. So first thing we look at is this, the plastic state, the moldable state. Well, what we expected of fresh concrete, but whenever I'm saying concrete, you can also take it for cement-based material. In case of concrete, of course, it's special because you have a lot of aggregate and they contain about 30% void. And they also do not conform to the shape because they're relatively dry. Normal concrete is relatively dry, but not all concrete. So these concretes are compacted by vibration. And as you vibrate, it must yield easily because you are giving some force, vibratory force. It must yield easily to deform under shear and also shall flow to attain desired shape, maintaining uniformity and cohesiveness. That means relative distance between particles should not change, uniformity and cohesiveness. Two aggregates, their relative distance should not change. They will deform, but this should be maintained. tensile strength should be sufficiently high, in fact, at the fresh state. So people, in fact, people have started looking at this even in 1950s for paste. There are literature available, book by Holiday, I think, edited book by Holiday. There are a lot of some literatures of 1950s available. Now, shear stress strain curve of concrete is important. We'll see that. So flow of fluid, of course, takes place against frictional resistance, that we know. Fluid, one layer will oppose the other layer. There are two layers, so there's a resistance against this movement if the flow direction is this, and that's what results in viscosity. And velocity gradient therefore would exist when liquid is flowing, because if this is at the more away from the boundary, then this will flow faster, this will flow slightly slower, and near the boundary it will be zero. At the boundary interface it will be zero velocity. So relative, there's a velocity gradient exists along this direction, normal to the direction of flow. Of course, you are talking of laminar flow, and the relevant property, the resistance, is defined in terms of viscosity. Cohesiveness, concrete shall not segregate, and that property is governed by tensile strength of fresh concrete. That's what I just said. So viscosity, tensile strength, these are important property. So for solids, we know, definite shape. It has got definite shape and volume. So when you apply stress, let us say shear stress, other stress also, but shear stress is more important for us because we are looking at movement of over one layer over another. Shear stress is proportional to shear strain. Liquid deform continuously under shear stress, right? No matter how small the stress is. And this is the relationship. For liquid, shear stress is proportional to strain rate, right? This is Newton's law of viscosity. This is the strain, shear strain rate. And proportionality constant is called viscosity. So that's how it is. And then you would have studied in fluid mechanics that tau is proportional to velocity gradient, because d gamma is nothing but, if I take dx as the x direction is the movement direction, and dy, that's the shear strain, and dy, dx, dy, dt, dx, dt is the velocity. So it's the velocity gradient. Y is the normal to the direction of flow. So viscosity is same, so viscosity. So concrete cement paste may stand in a heap if the water is low and flows when shear stress is applied. So when you apply small shear stress, it flows. So if you look at rheology of fresh concrete, a Newtonian liquid, tau is proportional to shear strain rate, right? And Newtonian liquid, this strain rate, right? Whatever the symbol is, my handwritten one, Newtonian liquid, 0, and it's like this. But material like concrete, of course, we'll see that self-compacting concrete is almost like this. So you have to apply a stress, right? So if you don't apply stress, 0 to 1 situation, you apply small stress, it doesn't move. You apply, for example, there's a piston which is applying the stress, pumping, let us say. So 1 to 2 is something like this, kind of a velocity gradient forms. And here velocity is 0 everywhere. Velocity gradient forms, and 2 to 3 is something like this. And then 4 is almost flowing like a fluid, parallel line to this. So you'll have viscosity here, plastic viscosity. So it's called a Bingham fluid. So fresh concrete is like Bingham fluid. You apply some amount of yield stress and then it flows. And you can see that for various concrete, standard concrete, that's what I was saying, that you apply, this is extension. This is a line extended. So straight line extended, it will be something like this actually, as I was showing. And this is self-compacting concrete, behaves almost like Newtonian fluid. And if you add more water, of course, this is the shear rate, but then this has been determined in terms of torque, rotating viscometer. So you have a torque, so you have initial torque up to which, after which it will yield, and then shear rate, which is the RPM, etc., etc. So it is proportional to that, and that's how it is. So that's how concrete has stress rate. For example, plastic viscosity, yield shear stress, these are the two most important criteria, as we have seen. So these are the two important property. If you look from the physics point of view, shear stress and slope of this line, these are the two important property, because this dictates how easily it will flow, and this is how much force you need. So you should require actually little force, vibrating force, and that should allow it to flow. And then it should flow, but tensile strength should be maintained so that there is no segregation. So that's what it is. Now, what you can see that this plastic viscosity versus yield shear stress, more water, viscosity reduces, shear stress also reduces. Paste is an important factor. If you have less paste, there will be voids in the system. Yield shear stress will increase, but viscosity will reduce. Less water, it goes, viscosity increases, yield shear stress also increases. More paste means there will be increase in viscosity, but reduction in yield stress. So various kind of material, fly ash, for example, pulverized fuel ash, because this spherical packs better. There are several things. GGBS is of course ground granulated, so it doesn't improve really from that point of view. Some dispersing admixtures, the plasticizers can put it in this direction, reduce down the stress as well as viscosity. Some cases it reduces down the stress, but viscosity it might increase. So that's the understanding. And you can see that various concretes, plastic versus yield stress. Normal concrete is somewhere there. Your stress, yield stress, and viscosity vary in this zone. Self-compacting concrete is there, right? Some flowing concrete is here. Yield stress is very little. Viscosity is somewhere there. Pumping underwater concrete and high-strength concrete is somewhere there. So various concretes or cement-based material system is somewhere there. And paste makes it plays an important role, because water makes the cement paste plastic. So if you add water, air-filled voids are occupied by water. And there's something called basic water content, which is achieved when all open air voids are isolated. I'll have a diagram. First, initially there will be air bubbles. You have particles, solid particles, and in between you have only air. This is only air, this is only air. But if you add water, let's say, let me put this color, water will now start accumulating here, and they will isolate the water air bubble, disconnectivity. Air bubble will not be interconnected. So a particular level, when air bubble gets disconnected, isolated, that's called basic water content. And this is a finding of T.C. Power in US, 1950s. And he found that the normal consistency, which Vickers actually empirically found using his apparatus, which is an empirical apparatus, corresponds to this water content. Right? So that's interesting. He came from theory and found it. So if you add more water, paste will become softer, and dispersion, cement will be dispersed, and flowability will improve. But you have to have minimum this. So water makes the cement paste plastic by progressive addition of water. Air-filled voids are occupied by water. Basic water content I have defined. Higher water makes it. So this is what it is. The diagram would look something like this. You have particulate system, solid particulate system, cement, fly ash, whatever it is there, powder. And you have water. When water forms something like this, The air bubble is colorless here. This is the air bubble. This is the air bubble. And it is isolated. So that's actually your basic water content or consistency. And you add more water, it becomes something like this. Bubble becomes smaller and smaller. There is lubrication, mobility increases. Typically for most of the cement between this. But this is physically the concept. Well, some algebra is there. Empirical algebra. You know, viscosity has been found to be proportional to a paste, found to be proportional to function of delta, and some people found it out to be proportional to, viscosity is found out to be in centipoise, is found out to be some function delta. Delta is a parameter representing distance between particle in micron. So if you have high water cement ratio, this distance will increase. It's 5 micron for a water cement ratio of 1.5. Something like that, And there's another formula, and this another formula is, this is the viscosity of water. This is empirical, e to the power minus b w by c. B and c are b, etc. B is empirical constant. Another formula is something like this. B is an experimental factor, as I said, and WC is water to cement ratio, and subscript N, this N, represent for normal consistency. And S is Blaine's fineness in specific surface. So people have tried empirical ones, not really from fundamental principles. Some equations are available. You get them in Sender Popovic's big book. He has collected them all, number of them. These three are there. So in concrete, paste forms the matrix where aggregates are dispersed. So you have the paste in which aggregates are placed. This matrix separates the aggregate and also holds them together. It separates, but at the same time holds it as lubricating material, enabling plastic deformation. So when you put a little bit of stress or vibration, this one easily deforms and it takes the solid along with it. So decreasing the volume of matrix reduces dispersion. If you have less paste, particle to particle separation will be less and particle interference will be more and stiffens the concrete. So you have to have sufficient paste in the system. Below a level, if you lower it, it will result in harsh and segregating concrete because it will not hold the aggregates. So aggregates will go out under jolting of travel. So that's what it is. And if you increase the matrix volume, it improves the concrete consistency, and matrix must be of adequate consistency. But if it is only of cement, the cost will increase. Low water cement ratio matrix may cause dispersion, but cannot hold the aggregate together because it itself is dry, it's not consistent, so stiffens. And if you have too much of water cement ratio matrix, then segregation, bleeding would occur, right? So thus segregation and low dispersion and low holding capacity. So aggregate will be there, water will go on other side. Normal concrete usually have water cement ratio more than normal consistency. That's what I just mentioned. So that's adequate consistency. Therefore, paste content governs the flowability. These properties like plastic viscosity and yield shear stress, etc. For reasons of economy, obviously, we used to put less, and typically this used to be 28 to 32%. In normal concrete, maybe slightly more. Higher paste content improves workability. Now, if you look at self-compacting concrete, which has got practically zero yield shear stress, should be, paste content is 38 to about 45%. Now here paste, can increase, cost may increase. So paste includes all cement sized particles plus water admixtures. So which means that cement, fly ash and similar other material, even inert material you might put, they will improve the paste. In high performance concrete, for another reason, it is about 50%. Paste content is 50%. Well, this is to control actually shrinkage. I'll not come to that today. So that's what it is. So you see that fresh concrete paste is an important issue, and water in the paste is an important issue. Now, what happens in vibration? People have done box shear tests, which you have done actually in soil mechanics. So you apply a normal stress like this, and shear stress. This is the surface. Shear deformation is delta over H. So if you plot shear strain, shear stress versus strain, they behave like this. Obviously, there is an yield as it starts moving. The friction, this is a frictional bond which will be there, which resists, and there's a plastic deformation. Now, if you plot many of them together from many such graph, different sigma versus tau is this value, tau is this value, tau is this value, tau is this value. You might have done it in soil mechanics, undergraduate level. So if you plot tau versus sigma value, you get linear curve. So yield stress is a function of, right, at any point tau is a function of tau 0, which is yield stress actually, yield shear stress, plus mu into sigma, where mu is 10 phi, which is actually something similar to your viscosity. And this is the tensile strength. This is the tensile strength. So people have tried this kind of tests also. But nowadays, of course, people are trying to develop rheometers based on the concepts of chemistry and polymer science, rotational viscometers and things like that. Now, if you apply vibratory load and then apply a normal force, you find that this curve comes down. This curve comes come down. Under vibration, what happens is, before vibration, the curve is something like this. After vibration, curve is something like this. And during vibration, it is something like this. That means there's a kind of liquefaction which occurs, right? There's a kind of liquefaction which occurs. And there's a theory behind that. I might have a touching up on that. So this is how it is. Vibrate, leave it, again vibrate it. So this is how behavior would be. So before vibration, during vibration, and after vibration it stabilizes. So viscosity increases. Now it is almost solidified, all put together. And yield shear stress also is increased. And therefore you can't really make it to vibrate again. Then it will be you will be damaging. So during vibration, actually what happens is, during vibration, yield shear stress, this is 0. And its plastic movement started like this, and finally this is the plastic movement. So vibration brings down the yield shear stress. This D point represents sigma A, called agitation pressure, the vibration pressure. If you extend this line, this is D dash, it represents sigma A, called agitation pressure. So actually it takes place in 2 stages. First, some air is driven. I don't think I'll go too much into it, but a little bit of understanding I'm trying to give. In first stage, vertical settlement of coarse aggregate takes place in a manner similar to packing of granular material. You have a heap. You have a heap formed like granular material. So when you start vibrating, actually there will be some packing. All air gaps will go away. From 30% to it might come 5%. And then second stage, concrete behaves like dense liquid, and air bubbles are removed from the surface, forcing water to appear in the surface. What happens is, the water actually, water can vibrate more. So I'll just quickly go. Water particle can vibrate more. Under vibration, water has more mobility, liquid. So water in the paste system tends to put excess pressure onto the paste or material boundary, causing aggregate system to move. Right? That's the liquefaction kind of a thing. So I don't think I'll go into that too much right now. Not part of my discussion really. So workability, now let's see, we have understood workability. Now workability is basically moldability. So one definition is the amount of useful work necessary to produce full compaction in a mold. So moldability. Useful internal work is a property of concrete. alone, although some amount of energy is spent in overcoming the friction between concrete and the rebar and formwork, etc., etc. So that's how we define workability, which you might be familiar. There are three components: compactability, function of the work done. So now I can come from my rheology, half tau 0 plus mu sigma, that's at any level, right, into gamma y. So stress strain, half stress into strain, because stress is yield shear stress plus mu into sigma at the level that you are operating. Sigma is the normal stress that you apply, right, which will be a self weight, weight of the lift of the concrete, no, concrete itself. So that into mu, that's the stress into the strain. So that's the work done. That's the work done. Now, can we quantify this? Well, we have to know all this if we want to quantify. At the moment, people are trying to develop, uh, measurement methods. Some are there, but it's not coming to code or something of that kind. Sooner or later, this science has to come in. Mobility is after that, which is related to viscosity. Obviously, yield shear stress has to be low. And it also depends upon maximum size of aggregate, because aggregate doesn't want to move, right? So this is what it is. Stability is function of strength, tensile strength. So this is again segregation. This is related to viscosity, and this is the work done at any stage. So I should be able to actually model it if I can, but at the moment we are not able to do that. There are some empirical equations. For example, one simple empirical equation is I into ln W, amount of water, into Y. Y is some of those empirical measures, plus K. A lot of people have tried a lot of empirical equations. They are empirical equations. And each equation varies from the other. There are 50 plus equations. They are in the book by Popovics, which I am mentioning here. Y is a slump and W is water. I is 10 for slump. So this will be different for different method they use for measuring. For example, if you use compaction factor, this I value is different. If you use what you call BB test, it could be different. So from this, one can find out if W2 is the water required for slump value of Y2, then W1 is the water required for slump value of Y1, or vice versa. So you know one and corresponding slump, and your required slump is known, you can find out what is the water demand. That's the kind of relationship. Easily is simplest of all. There are many such similar. Sander Popovic's book, Quantitative Methods in Concrete Technology, Volume 1, gives you 50 plus equation, some for, paste, many for concrete, and none of them are same. They don't give same result, because they're all empirical, done by tests, done by different people at different place, different conditions. So not based on theory. But if it is based on the physics that I talked about, so can this work be modeled? So you have a scope of doing work in this. Think of doing work in this, you'll enjoy it, surely. At the moment, I don't have mathematical description of it at the moment, but at this level, at the previous level, it stops. Let's come to aggregate. Here we have something to do. Some algebra is available. Let's see. Aggregates are inert material. They form the skeleton of concrete. And we'd like to minimize the volume of paste. That means aggregate must be packed well. Maximize the aggregate volume fraction. And this interstitial void space in aggregate system is filled in by paste, but it alters it also, because it pushes it out. And interstitial, so it's desirable to minimize aggregate porosity. Now, this porosity or void content within the aggregate system, we'd like to minimize this. We'd like to minimize this. This we'd like to minimize. This we'd like to minimize. Now, if you increase the size, if I have larger size like this, and use the next size, let's say somewhere there, this will go inside this. Same size void content doesn't reduce. For spheres, it will be 48% with simple cubic packing. If you put finer and finer size, they will still go inside and reduce the void. So more the number of sizes, because your fine particle bottom line is 75 micron. And we use a quotient 2 because these sizes are in geometric progression. So 75 to 150 to 300 and so on. And if you go on, so this is 75 to 150 is one size, 150 to 300 another size, and so on. And if you go up to 20, you'll have about 8-9 sizes. You can count this. But if you increase one more size, 40, the voids will reduce, because all this will go inside the voids of the 40 for the same volume, total volume remaining same. So if you add one more size, voids reduce. I don't think I'll go into details of this again. Overall voids in the aggregate thus reduces by increasing what we call maximum size of aggregate. Paste required will be less. And that's why in mass concrete, where strength is also not required, and you can use 150 MPa, 150 mm aggregate, paste content is much low. So because they just pack it. Shape is an important factor. Spherical particles pack better compared to irregular shape. All these irregular shape, they would have voids in between. But spherical particle packs actually better. Right? So natural aggregates are not spheres, but they're rounded, irregular, or crushed. So crushed are they would pack least, they will pack best. Now shape you can define in terms of called angularity factor. I'll quickly go through this simple algebra. Ratio of specific surface of size group. To that, let me define this. First I thought I'll not, but finally I decided. You can define something called volume diameter of irregular particle like this, having same volume of the particle. So if the volume of the particle is Vp, pi d cube by 6, same volume for the sphere. So this is called volume diameter. 6 Vp divided by pi to the power 1/3. This is called volume diameter. Surface diameter or specific surface diameter should have same, 4 pi, pi d square should be equals to surface S, I think I'm using surface of the particle. So you can see that AP, sorry, I'm using AP. So AP by not 4, pi to the power half, that's called surface diameter. Surface area is same. And specific surface diameter is the diameter of sphere having same surface area per unit volume as the irregular particle. So for irregular particle, it will be Vp by AP, AP by Vp will be a specific surface, and for spherical particle, it will be d by 6, as we shall see just now. Volume diameter, so it will be d by 6. Specific surface of sphere is pi d square, so d by 6. So when I equate this to, I get specific surface diameter of 6 Vp by AP. Now, this is used to define sphericity factor, which is the ratio of specific surface diameter to volume diameter. So look at that. 6 Vp by AP, which is ratio of specific surface diameter, to, this is the specific surface diameter. Last time we just looked at it, and this is the volume diameter, and this is your sphericity factor. And 1 over this factor is called, we just found out right now, this is the specific surface diameter, and this is the volume diameter. So ratio of this is what is this. And for sphere, it will come out to be 1, as you shall see. So for sphere, this is VP is this, AP is pi this, so this comes out to be 1. For cube, you can calculate out. For cube, you can calculate out, it comes out to be 0.806. For tetrahedron, this is 0.53. And this is angularity factor is 1 by xi. Is a reciprocal of sphericity factor, right? And if it is 1, that's the least angular. And if it is higher, then angularity increases. So values of angularity factors is 1.1, 1.4, 1.7 for rounded, irregular, and crushed aggregate. And this has been observed by people. The void content of aggregate is linearly related to angularity factor. So void content will increase for a given type of packing. Thus, rounded aggregates requires lower paste because they will pack better. Packing density then is the volume of solids in the unit bulk volume. That's what we define packing density. Let me introduce the new concept. It's called packing density. So in your aggregate system, P is the porosity, 1 minus P is the packing density. So packing density of single-sized particle is relatively low and depends upon packing arrangement. If you have simple cubic packing, that means one cube like this, another cube like this, and on top of another sphere, another sphere. This is called cubic packing. So you can find out the porosity. This will be simply d cube minus pi d cube by 6 divided by d cube, and which will come out to be 1 minus pi by 6, 1 minus pi by 6, and it will work out to be 48%. Pi by 6 is 3.14 divided by 6, 1 minus that will give you 48%. So if you have simple cubic packing, so density of simple cubic, body-centered cubic and face-centered cubic arrangement will have packing density 48% void. So 1 minus 48 will give you the packing density as 0.52. And if you have kind of a face-centered cubic, you can get 0.74. That's the maximum you can get. Actual packing density of single-sized spherical lies somewhere in between because they are neither cubic nor face-centered cubic. Some random packing even might be slightly lesser than this, but you normally find it better than this. But if you have multiple sized, then the packing will improve. That you can see that. So proportions of different size fraction will be also has to be appropriate for maximization of packing density. Supposing I have a binary mixture, it can be easily seen that packing density increases with addition of another size material. Just let's see this right now. And degree of improvement depends upon size ratio. So packing of binary system can be easily understood. That's what we are trying to do. And then the equations I'll give you for multinary systems and all, which are some of them are very recent concepts. For example, you consider two aggregates, A and B. B is coarse, A is fine. Spherical, we have taken it for simplicity. Okay, I'll just go to the next one. That would look better. Then I'll come back. That will go inside. Okay, just let me go back then. Fine. So consider this. No, not this. This one. Previous diagram. Right. Consider this. Right. So this is a finer one. I put A here. Some quantity, very small quantity. And just I have added. So now total volume would increase by this amount. Right. So this is A. B is coarse, A is finer, so I've added B. Now void ratio is defined as a volume of solid, volume of pores divided by volume of solid. So volume of pores divided by volume of solid. Volume of pore is here, volume of solid is here, divided by volume of solid. So one can write this as B by Vs total volume by Vs minus 1. VPBs are volume of pores and solid, as you can see. And when I've added them, put them together, they look like this. Total volume would increase now. It's bigger now because this has gone inside. Right? I've just put in hypothetically anywhere. You put anywhere, total volume will increase. But in the process, pores here are reduced. Otherwise, supposing I just would have increased the volume with the fine particle alone, there would have been pores inside. So that has got reduced. Right? Now, void ratio alone of A is given by this. Void ratio alone of B is given by this. So if you add small volume, packing of fines remaining undisturbed, supposing there is no disturbance, total volume would actually reduce. So volume fraction of B, let us say, is given by this. Volume, I'm talking all of volume, not mass. Volume fraction, right? Volume fraction is this. And now void ratio will be, because we said total volume divided by volume of the solid. The VV is the volume of the solid because that's what I have added. Total volume has increased by this, minus 1. So I can write it like B by VSA, separate this out. And, separate this out, putting them together, just algebra, a little bit of minus, if you subtract, VSA will come, V minus VSA will come, V will cancel. And then B by VSA I have taken out, it will be something like this. You can show that it's something like this by this algebra. Now, what is this? What is this and what is this? This I can take common. So if I take this common, this is proportion of A in the system, and then I get this simple algebra because I'm just taking this common, right? I'm taking this common, so I'll get 1 minus, this can be written as 1 minus VSB because this minus 1, so it will come out something like this simply. Because 1 minus VSA is nothing but BB, VSB, solid volume of VSB, right? So one can write it in this manner. So void ratio, and this is X, that is your proportion that I have added. So e to the power X, and you can show that algebra by algebra, simple algebra, that it looks like this: V by VSA 1 minus X plus X minus 1, or in other words, it can be expressed in terms of void ratio of A, EA 1 minus X. So it linearly reduces. You can do this algebra yourself, no problem. I will send the PPT in PDF format. You can try this out later on. Now you add small amount of fines in the course. They will simply go inside and reduce down the void. Then you can do the same exercise again. Divide both sides by VSB by VSB. Earlier you have done it with VSA minus 1, and this is nothing but X is the volume of B, because that's what I have defined, volume of B as X. So EX is equals to, again you'll get a linear relationship. EX you'll get a linear relationship, right? So you'll get a linear relationship here, and if I plot this, they'll look like this. They start from void ratio of A when A is 100%. It reduces linearly, and EB this also reduces linearly. If I start from EB in the coarse, I put the fine, come like this. In the fine, I put the coarse, I come like this. From both sides, go on adding. Somewhere they cut. After that, it will be other around, right? So this is how it is. Somewhere they'll cut, but actual behavior is found to be something like this. For little portion it matches, then it doesn't match. So thus Ex can be represented by two lines intersecting at X star, and you can find out this X star value also simply by equating the two, and you get this expression. EA, EB can be easily found out. So the optimal proportion you can find out if there are nothing elsewhere happening. But actual behavior is represented by the curve. By and large, this is close to this, not same. Minimal point is close to this. Packing density is 1 minus P, and P is the porosity. So you can get the packing density also in this manner. And the curve, you'll get something like this. You'll get something like this. But actual packing density will be somewhere there. It will not go up beyond a point. It's supposed to go at infinity, in fact, ideally. So for so this is how it is supposed to be. Now why doesn't it match? So we call it A dominant case. A means fine dominant case. B dominant case. All these expressions can come in the same manner. You can find out the packing density. Algebra is simple. I don't think I'll go too much into the algebra, then I'll be spending too much of time onto this. You can look into this. Right, this is available in TC Power's book, Fresh Concrete. So B dominant case, similarly, you get something like this. So packing density, you can find out expression for packing density. But in reality, the curve is slightly different. That's called particle. That's because of what is called particle interference. At the wall of the coarse aggregate, fine aggregate don't pack as they would have packed here. There will be voids. This is called wall effect. And when you have a fine aggregate coming inside, the coarse aggregate, it pushes them out. Particle interference. This is called loosening effect. So these two effect actually causes. So this is your coarse aggregate. This is your fine coarse aggregate. This is the fine aggregate, and this was original. Now there's a loosening effect and wall effect. Wall effect, it doesn't pack well. Loosening effect, they actually push. So total void actually increases. So actually something like this diagrammatically you can show this was ideal, no loosening effect, and this is the real, and you can take care of loosening effect and particle, then it will be something like this, right? This line is fine. This line is fine. You take care of loosening effect, etc. Actually, you'll find that something diagram comes something like this. Yeah, loosening effect, and this is wall effect. We'll bring it here. So that also too much linear. So this is wall effect, this is loosening effect, but this has still remains same, almost, not exactly, too far different. So you can actually find out the proportion at which it will give you maximum packing density or minimum void ratio. So that's some algebra, right? But this has been extended quite a bit in recent times by people in powder technology. So they call it virtual packing density, ideal case, and then real. So ideal case is virtual. Let their proportions be R1 plus R2. So virtual packing density is defined in this manner, coarse dominant and fine dominant. Their virtual packing densities, ideal and real, are something like this. Void ratios expression I have given you, and one can do this exercise same using slightly different notations. I've used different notation for this ones, and it comes out to in the same. So if you take loosening effects and all, you get additional factors. You get additional factors, which is there's a constant coming in here, which shows the effect of 1 on 2. A12. So this is one can get the expression for packing density in this manner. A12 and similarly A21. One talks about the loosening effect, another talks about the wall effect. So effect of 1 on 2. So fine dominant system. 2 is the dominant aggregate. So that will have loosening effect. That will have wall effect. So wall effect will be there, and that will call it 2-1. So there will be a B2-1 constant. So this loosening effect and this one can be taken into account. Simple algebra, there's not too much of complication involved in this. They are taken in the linear manner, just with a coefficient. And you get the packing density expression in this one. For binary. Right? So for binary mixtures, you can actually get packing density overall. And similarly, for fine dominant case, you can get it like this. You can derive these expressions. Right? And that's what it is. Actual packing density. This is ideal packing density. That means single case. And this is the ideal packing density of the single case of the coarse, and this of the fine. So for optimal packing, you can sum it up and you can find out, provided you know this one and this one, the loosening effect coefficient and wall effect coefficient. For complete interference, A, B equals to 1. Is this, A, B equals to 0 means no interaction, depend on size ratio. If the size ratio is too large, too different, one is very large, another is very small, the interaction would be relatively less, and it depends upon the size ratio. So size ratio versus B to 1. That's your wall effect coefficient. People have actually empirically related them. It comes out to be something like this. As your size ratio becomes same, there will be obviously no effect. The effect will be 1. If you have complete interference, they will separate out. For very small size ratio, it would actually be less. Similarly, for loosening effect, also, size ratio 1 means maximum effect. So these coefficients people have found. And they have given empirical formula based on these two equations. I have taken binary mixtures only so far. This algebra has been actually extended, and binary mixtures. Okay, the compaction method also, affected. And there's a compaction index. Packing will depend upon compaction. Phi is for ideal packing. And if you know, this depends upon the proportion of those material, fine and coarse, for binary mixtures. K1, K is given by beta plus, etc. There's some beta, I'll just define what this is. It's given by this formula. K is given by R1 by phi1, R2 by phi2, etc., etc. And these coefficients are given. Compaction for pouring, 4.7. For optimized vibration, this is 15. For mixtures, all concepts can be combined and solved for gamma. So for mixtures, gamma total overall gamma can be solved, provided gamma 1 is the ideal, or without that compaction, ideal compaction method, ideal cases, proportions are known. So you can solve for this. So E, this is what it is. Void ratio is given by this. For multinary mixture, this concept can be combined. And there are much more complicated formulas which I did not actually show. So the point is that actually the generalization of packing density is possible, but there are too many empirical constants. For example, A1, 2 or B2, 1. These are to be known to me. And there's a book on the whole thing by Franco de Lerard. Franco de Lerard in my English accent, but French, they call it Duluru. So in their accent, it is his book. He has written a book on this. But you go to powder technology, you find a lot of such models. CPM, compactable particulate mixture models. So this, this model. The more complex, I don't think I have included that, or maybe I have included that. Let me see. So right? So that's what it is. So that I didn't include this. I thought I'll include, but I have not. Anyway, so there are a lot of, this is this model, but there are a lot of empirical coefficients actually you have to verify for your aggregate system. So that is a deterrent, but for very high strength concrete or such concrete, you better do it because economy is also an issue and your requirement is also an issue. So this is why mathematics is being used in mixed moldability, designing the cement-based matrix. I'm talking of ultra-high performance concrete or self-compacting concrete to anything. The packing concept can be applied. I have given you examples of binary. You can go to multinary and complexity. I had the equation, but I think I have not given it. Is better. Okay, if you have anybody is interested, I can pass on those material to you. Or I think somewhere in my some lecture notes they will be there also. Class lecture notes. Okay, so that was one thing. Now let's see strength. What is the mathematical generalization possible in strength? When I'm material, I'm looking at material. This is material strength is the ability to withstand applied load without failure or plastic deformation. Often, I mean, it will depend. You test it on samples. Failures essentially means separation of particle or fracture. Now, bonds usually resist separation. In a particulate system, bonds are, if they cannot be inert material, so they will not bond chemically. Aggregates are inert. They don't bond chemically. At best, you can have some sort of secondary bonds in some cases, but usually it is mechanical, roughness, friction, and other material coming in, filling in this gap. So roughness is important here. Now this bond is not very strong. They're weak. But if you push the particle from all sides, it doesn't cause separation, but pull does. If you pull, it does. For example, this is your material. Push it from all sides, triaxial. You can't do much. Only voids will get filled in. Now try to pull them, uniaxial pull, right? So it follows from here, the next one, will fracture them. So pull can result in failure, material separation, push does not. And this particulate matter where the bond is not very strong, these bonds are not very strong, they are mechanical. Unlike metal, you have a metallic bond. All nuclei work together and outer electrons, they pack together. There's the best packing with little pores. They're not in crystals, they will not have pores actually. They pack it and they form the crystals. So you can't separate them out. But they have defects. Those defects have, bring down the, what we understand as strength. Right? So metallic bonds are very strong bonds. Right? The outer electron acts as cloud cluster, they can move, that's why they are good conductor, etc., etc. But these are particulate material, you are bonding them, they don't form the way metals are formed or alloys are formed, where crystals are formed after cooling from heating stage. They are polycrystalline. Here it is not like that. So therefore they can be separated out easily and they fail in tension at much lower force than compression. Intermolecular forces, they are there, Van der Waals forces. They are also known as London dispersion forces. They include momentary attraction between molecules because center of positive ion and negative ion, they don't match quite often. So electrically charges, covalent compounds, covalent molecules or compounds, these don't match because electron sharing is happening. So you have got, dipolar, polarity would be there, and therefore electrostatic. And these bonds differ from their ionic. You don't see mostly in ionic bond in this material, but in covalent material you see them. But these bonds are not stable and caused by polarization particles. They are actually residual bond results from separation of electrical charges. Hydrogen H2, O2, these are all covalent bonds. But when you make H2O, these charges, their separation occurs. Thus, dipoles are formed. Bond within hydrocarbons, CH4, is covalent. But if you have a polymer where you have got C, H2, another H, and another C, H, H, and so on, long chain molecule, these bonds are all covalent bonds. But I have one molecule and there is another molecule, H there, another chain, and there will be residual charges here and there, and the bond between these two chains would be van der Waals kind. That would be van der Waals kind. Right? They are mechanically very weak, elastically deformable, poor conductivity, obviously. So H2O is something like this. So positive charge, negative charge, they don't coincide and forms dipole, right? And therefore they get attached. Water molecule gets attached. And that changes, direction also changes. So theoretically one can calculate out this bonding energy. And you find that strength estimated on the basis of this energy is gross overestimate. Because there are defects in the material, flaws in the material. And in cement-based materials, these are actually pores. This is what we saw. So it's macro homogeneous at centimeter level, right? Macro homogeneous, sorry, at not centimeter, 3 times the aggregate, 10 centimeter level, right? So heterogeneous at centimeter level because you'll have aggregate which are heterogeneous, centimeters, mortars which are still finer. And you go finer, micro and finer levels, it's always heterogeneous. And we know that chemically combined water, people have done experiments long back. Chemically combined water with cement, OPC cement. These are the compounds of cement. And this takes this much of water for 100% reaction. This takes this much, 100 grams of this takes this much of water, A2 amount of water for 100% reaction, and so on. So you can actually calculate out the, bound water. You can calculate out knowing the proportion of C3S, C2S, C3A, C4AF, or knowing A3A4, which has been determined by people doing very long-term experiment. This was done, I think it was done in France, if I remember correctly. I don't forget the name of the scientist, but this is available in Soroka's book. So you can see that they have done experiments up to 13 years. And they found out this A1, A2, A3, A4. And the quantum of water that reacts is somewhere like this. So if you know the proportion of C2S, C3S, C2S, C3S, C2S, C3, etc., you can find out what is the average amount of water you require for complete hydration of cement, 100 grams of cement, provided you are allowed to do so. Hydration is complete. So these products are formed, and we know it's around 23%. 100 grams of cement requires 23% grams. Just a minute. Maybe it's missed. I missed this word. So this comes out to be, this will approximately comes out to be 23 grams. 100 grams of water, or 0.23 in this case. 1 gram of cement will actually require 0.23 grams of water. These are the products formed. Macro level properties are governed by the pores. There are a lot of pores in the system, we shall see, and performance of the pore-free solid is governed by this chemical. This is what the probable structure of cement paste given by TC power. Capillary pores, these are called large pores, and there are finer pores inside called gel pores. And these are cement, hydrated cements are layered structures. CHS gel structure, they are gelatinous material. And you can see that a typical backscattered electron microscopy image also. This 10 micron, so 100 micron. You know, it's 100 micron. If you look at 100 micron size, you'll find unhydrated cement which will look white. Pores will look black because backscattering doesn't occur from pores, so they're all black. And rest all are gray. Hydrated phase is gray. So if you separate out the pores, you'll find actually they're all black. I think I have left that. So you'll find a lot of, you know, the black ones are plenty of black ones. Plenty of black ones. And that is, yeah, this is the binary image. Separated out the black ones. They are the pores. So pores looks like this. All random shape, size, everything. But between the cement particles. Cement particles here, hydrated particle outside. These are unhydrated cement particles. So that's the kind of model people assumed also. And eventually density of hydration product is something like this. Density or specific gravity of cement is 3.15, but the hydrated cement has got much lower specific gravity. So they occupy more volume. And from that earlier hydration, complete hydration I was showing, 100 grams of cement chemically combines with 23 grams of water. And one can do a little bit of calculation, and you find that the volume of the hydration product is less than the original product, original cement plus water volume. Those are called empty capillaries. Well, and this solid product which is formed, this has again got some pores inside like gel pores that we have seen earlier. So 2.51 is actually only solid, but 28% is still pores which are, you know, inside. So actual solids have got 1.78 or something is a specific gravity. So this can be schematically explained like this. Gel is colloid sized particle having 28% characteristic porosity, which has been found out by BET kind of test. Right? So this is a book, Igor Soroka. You get all this information there. And these gel pores, fine pores are responsible for shrinkage and crisps. Capillary pores actually reduces down the strength and also related to durability. And there are larger pores because of air entrainment. And if you have poor compaction, additional pores will be there. So you have pores in the system inherent. Specific gravity of cement is 3.15. So this will be the original volume if cement is C and W is the amount of water. And some of it will hydrate. So proportion of hydration is called degree of hydration. So CH gram of cement will react with 23 CH gram of water, produce this gram of hydration product. The volume occupied will be this much, and original volume, 28% of this is gel pores. So if you multiply it by 20, etc., you get this one is the gel pores. Mass of unhydrated cement is something like this, and volume of empty capillaries is something like this. Same equations, not very complex and not instantaneous. So what happens is when you add cement to water, solid forms within 30 minutes, almost, setting. But all pores are not filled in. They get filled in later on. Solid skeleton is formed. Now these pores get filled up as the hydration progresses, and porosity, internal porosity reduces. This takes time. Now, original water filled space will get filled in, provided you are able to supply water continuously to the system. That's called curing. That's called curing. right? That's called curing. This is how it looks like. This diagram will explain everything. This is your cement particle. I've assumed it to be a sphere. This is the hydration occurring, the hydration product surrounding, right? And these are called outer product outside the original grain boundary. This is unhydrated cement, and this is some calcium hydroxide precipitates, reaction product, more hydration product, but still some space will remain vacant, and they form capillary pores. They form capillary pores. They form capillary pores. So they form capillary pores. So around the cement unhydrated product, you have hydration product and the pores that we have seen from backscattered electron microscopy. You know, like this is what it is. It shows unhydrated cement, calcium hydroxide outside. The red one is the inner product, green one is the outer product, and 2-3 of them, if they join each other, then very good, no pores. But if they don't join, there will be pores. And finally, you can have structures like this. Black is the unhydrated cement here. This is a computer generated one. You know, they do some modeling, simulation modeling. They put 10,000 particles, spherical particles, simulate the chemical reaction, right? And then also randomly choose the location of the hydration. So you can simulate them, and that's called, you know, microstructure simulation. Mike is one such model. And you've got different products, calcium hydroxide coming in somewhere, and if they join, that's very good. So these are the calcium hydroxide patches. They are supposed to diffuse. Dispersion, diffusion is occurring through the fluid, that is water, and they, whenever they meet the same particles, they get touched, and so calcium hydroxide or precipitates or something like this. So this is a simulation one. And porosity reduces because originally water filled space get reduced. Porosity reduces. Solid products, different kind increases. I don't think I'll go into the chemistry. So this initial period is called dormant period, which is your initial setting time. Then the full solidification around 10 hours final setting time. Then pores gets reduced, and actually this is called hardening because strength gain will occur during that period. Some product change to one product to another. For example, etringite changes to monosulfate. I don't think I'll go into this unless you have some question related to this. And that's how the same model I was showing looks like. So initially like this, particle and water, hydration product, outer product coming as fibers, joining them, and that's what it is. So all this, I can calculate out the porosity of cement paste based on the Powers model. This Powers model actually, water and cement. Part of it is hydrated. This has not hydrated. CH gram is hydrated. This is a hydration product, solid product of hydration. But its volume will be slightly less. And gel pores, it will contain some additional 0.19 CH gel pores. Remaining water space, filled space, they are called capillary pores. And some empty capillaries. So using the stoichiometry, one can calculate out the capillary porosity and also the gel porosity and the total porosity. So volume remains same. This is the original volume. This is the final volume. They will remain same because volume is conserved. They remain same. So that's total volume is something like this. They solidify quickly, and this pore filling takes place inside pore filling. This water, if it is consumed further, volume will remain same. They will only increase this and this. This will get reduced. This will get reduced. So therefore, there is porosity. One can calculate out simply from this model. I don't think I'm going into this. I'm simply giving you the formula. Derivation is very simple. So volume of capillary water is this, and at any degree of hydration, so porosity you can find out, and total volume of total initial volume, so etc. etc. Initial volume we know is this. You know, if I divide everything by C, it is around 0.317 C plus W by C. So what you see is the capillary porosity is a function of water cement ratio. More the degree of hydration, this will reduce, and is also this is related to water cement ratio. Now, if I put this equals to 0, I get maximum degree of hydration because the after that will not have chance. Gel porosity is given by this, right? Total porosity is sum total of this. But if I put this equals to 0, I get maximum degree of hydration as this because there will be no space, capillary space for hydration product to occupy. So this algebra is very much there, right? And you can find out. And sorry, this is what happened to this? The total porosity versus water cement ratio. This should have been connected. This should have been connected, or this has gone shifted here. It would have been something like this. This has been something like this. Got shifted here. Doesn't matter. This is something like this. So below this 0.36, below this 0.36, erase out everything. Right. And then do this. Oh. Yeah. This is showing from 0.32. So below this, no capillary porosity. Here we'll have capillary porosity plus gel porosity, because you can't have water cement ratio 0. My hand came and touched. So so that's what it is. So this is showing the capillary porosity from calculation. Bonding action, theoretically one can calculate out. It comes out to be this much, 7 MPa per meter square. Surface area is very large. Specific surface of cement is very large. So if you multiply this by meter square of the surface area, you get very high strength, right? So that's actually is not the strength. So strength of the paste is van der Waals forces between gel particles. So between gel, of course, there is van der Waals forces because they are layered structures, layered structures as we have seen, and there will be van der Waals forces. But layer to layer, another layer somewhere there, this force is not van der Waals forces. Layer to layer, sorry, this CHS C2S2H is covalent. Between CHS is van der Waals forces, and capillary pores, of course, there's no bond. So strength as calculated based on the bond strength comes out to be this much higher. Therefore, this strength reduction is attributed to existence of pores even before when you have applied the load. So if you apply tensile load, then from Griffith's concept, cracks will propagate spontaneously when rate of strain energy release is higher than the rate of energy required to create new surface. Now remember I talked of fracture. So you have created new surface. Every surface is or interface is associated with the surface energy. So if the surface energy required is less than the strain energy supplied, fractures will propagate spontaneously around a pore or a flow. That's the concept. So actually from theory of elasticity, one can calculate out the strain energy, rate of strain energy release, and rate of surface energy required. And this diagram explains it. Now we know the failure of cube under tension will be something like this. Uniaxial tension, uniaxial compression, you will have cracks along transverse direction because tensile forces are acting. Biaxial compression, it will be something like this. So in this, the cracks, in case of uniaxial compression, cracks are parallel to the load. Compression, cracks will parallel to the load. Actually, there is tension along this direction. Transverse tension, Poisson's effect. And it can take much less tension. The bond is not there, mechanical bond. So therefore it will fail. And theoretically one can derive this critical stress. Surface energy, strain energy release, which is a function of an elliptic hole that I mentioned earlier. This is 2c, already crack existing. So it's a function of 2c, and it has been found the half pore or pore radius or half crack width, crack length. T is the surface energy, E is the elastic modulus. But in concrete or cement paste, you'll have too many. So this is called critical tensile stress, elastic modulus, energy required to create new surface. 2 COL is the crack length, or 4 plus crack length. That's what existed. Now in concrete, you'll have too many of them. In concrete, you'll have too many of them, required energy, and each one will supply. So wherever this slope matches, so what we have seen is strength is a function of porosity and pore sizes. This size, this size, this size, this one, which is related to this. So if the cracks was not there, even this pore would have been there. So this would have been simply, you can say, approximately a kind of some kind of a radius, function of radius. So one can actually find out that it's inversely proportional to some sort of radius. But E and T, E is actually that for the solid. So in a simple form, one can write E is equals to E0 into 1 minus P, and T, surface energy required, T0 into 1 minus P. If you put them together, then you get something like, you can actually get an algebraic equation like this. And this is an average pore size, because pore size is very logarithmically. So volume weighted pore size, which can be found out from various experiments like mercury intrusion porosimetry, and strength is a function of this equivalent radius or mean distribution radius, and it's a function, of porosity in such a manner that as porosity increases, strength reduces. It's inversely proportional to the pore size or some sort of mean pore size. So that's the idea. This is sigma T. Sigma C is a function of sigma T because failure is due to tension. So this is why all these constants are coming, and one can relate this, so one can write like this. Sigma T is something like this, and take ET, E0, T0, pi, etc. out, somewhat equation like this can come. So one can write this, compressive strength. So this is some sort of a possibility, but this function is not final. This is an approximate way of taking kind of an average pore. There are many pores, some number of pores may be many. They might simultaneously start fracturing. So there are complexities involved. So starting point can be this model, but one can model this process and verify with the experimental results. That's what it is. But we have found out a way to find this, derived an equation for this. This is easy. This already we have found out from Power's model. This we have found out. So E and T are pore-free solid. Higher E, higher T, strength is more. Higher porosity results in lower strength, higher water-cement ratio. Higher porosity, that's what we have found out. Larger the pore sizes, lower the strength. Higher water-cement ratio, larger is the pore size. Why? You can see that now. Because let's say this is my hydration occurring, which I have shown earlier. 2 particles. Too much of water means too much of blue things to be filled in. Now hydration product, the inner product and the outer product has gone like this. And further hydration of this particle might cause it to join, or less hydration is stopped. These 2 particles are closed. This is the pore size, capillary pore size. This is the capillary pore size. Now if you have too much of water, these sizes will be larger. If you have too much of water, these sizes will be larger. These sizes will be larger. So higher water-cement ratio, larger will be the pore size. Right? So let me now erase this out. So pore sizes 2R would be Something you can guess, this visualize. But exact values is complicated modeling, and also verifying this by instrumental method. Less water means less space to fill and less capillary pores, lower R for lower water cement ratio. But C would not hydrate. So hydrates just minimum hydration, everything inside, a lot of unhydrated particles. But that's not dangerous, that's better because this is stronger. This is stronger than this one. This has got higher E, as we shall see. Now we have actually generalized the pore size distribution. Right? We have generalized and we have got an equation of volume of pores at a radius R given by porosity. This is a median radius because this cumulative radius, hydrated volume, one can talk about cumulative volume. So phi corresponds to cumulative porosity by the total porosity. So this is also volume fraction or porosity fraction you can talk about. This is a median pore size. This is cumulative distribution, and actual one can get this kind of median distribution, porosity, etc., etc. This is the cumulative distribution verified with number of data and established this. And then we have related this to mixed parameter like water cement ratio, age, diameter of the cement particle and all that. And these are the relationships are. If L is the total volume, which will be a function of the cement diameter, equivalent diameter of the cement, some K times multiplied because we don't know the shape, and the volume of the water, and equivalent to put the densities there very much. This diameter of the cement, this is the cement specific gravity, this is the water specific gravity, W by C, etc., etc. So one can get some sort of an equation. And if I know the degree of hydration, then I can actually, and degree of hydration has been related by an expression by empirical measurement. This is similar to many other people's results also. So W by C is the water cement ratio, LNT, HT is the age, and this is a constant. So at any degree of hydration, one can find out the size of the capillary pores, which will be the space between two hydration, extreme hydration product, total volume of cement plus hydration product is known. So gap between that, from that you can find out. That means this portion. After hydration, so this is the equivalent radius of the capillary. Entry radius of the capillary, you can find out geometrically. And we have arrived at this relationship. Arrived at this kind of relationship. R capillary relationship, something like this, from cement particle, average diameter of the cement particle, water cement ratio, age, etc., etc. Similar information you can generate from sophisticated simulation model, like the one I said, Mike or similar sort of thing, where they take 10,000 particles of different sizes. But then finally, finally if it has to be related to strength, you have to see how you relate them. Actually, the solid particles, if you know, then their modulus of elasticity should be known and things like that. Perhaps the models will go in that direction. So the mathematical modeling is possible. Now this is our model, in which we also found out a relationship, empirical relationship between gel pores, which is also a function of water cement ratio. Higher the water cement ratio, more gel pores, function of age. And this constant we have actually worked out. So total porosity you can find out, or total median pore size you can find out by geometric mean, where P capillary, porosity, weighted, geometric weighted mean. So porosity P, geometric mean, because arithmetic mean would have been simply this plus this multiplied by this, plus this multiplied by this. But the geometric progression we assume, because pore sizes are in geometric progression. So taking this, I can find out the mean radius, mean or median pore radius. Now, people have done nano indentation, found out the distribution of E along the surface space. So E of CH, E of CHS E of unhydrated cement. Now the future is to combine them through a model to obtain effective A. This has been very complex, not easy. How do you combine them? For example, if you see elastic properties of, cement clinker, right? Various compounds, you find the elastic modulus is something like 135 GPa, etc., etc., right? So average clinker would give you 137 GPa, gigapascal. Steel is 200 gigapascal. Average clinker or cement particle, unhydrated cement particle is 137. Let's see the hydration product. CHS gel, the after hydration inner product is 26 to 33 with average 29. And the one which goes outside the boundary is only 19.5. And calcium hydroxide is 35. So you can see that this is much less. Therefore, unhydrated cement is stronger. So if you have unhydrated cement and some hydration product, more the hydration product, E will be less. More the hydration product, E will be less. So it's not necessary that you have everything to be hydrated. This must be understood. And surface energy, we have found out very little more. No experimental results except one. So E of clinker is this, CHS is this. This is strong. And if you have bonded, they're like, aggregate, as if they're aggregate bonded. So material models, these are simple models. Matrix phase, particle phase, let's say 2G, two more models. We want to find out they're in parallel. They're parallel, right? The strain is same, but modulus of elasticity is different, so stresses would be different. Stress in one and the other will carry less stress. And if you find out the force P1 plus P2, sigma 1, 1 minus G, sigma 2, etc., etc. So E will be given as E1, 1 minus G into E2, because strain would be same in both of them. So E can be written like this. Volume of aggregate, volume of paste. Or volume of hydrated cement and volume of the, let's say, unhydrated product, and let's say CH, CSH, etc., etc. But if you assume them to be in parallel, the formula becomes something like this. So this gives, because now the stress would be same, strain will be different. And now this gives actually two bounds. It's been very difficult till date. I do not think there is any model which can predict this. So there's a possibility of doing good lot of work on this. Come out with the mathematical model. In any case, strength is a function of water cement pressure. And that's why the Abraham's law is so valid. We could generate from our model Abraham's law back again for various pastes. But in concrete, you have additional porosity at the interface of the aggregate and paste. Something like this. This diagram will give you. Paste aggregate bond. Aggregate particle paste. So these are mechanical bond. There will be air bubbles here trapped. There will be more porosity, wall effect. So all, and shrinkages here, no shrinkage in this side. Hydration from that side, hydration this side is little. This is around 30 micron. So this added additional pores. So these pores are additional pores. And we don't know how to quantify them as yet. Capillary pores, mesopores. This is in paste. And in concrete, you'll have additional pores in ITZ called wall effect and one-sided hydration growth, shrinkage and trapping of bleed water, all these causes. So bulk paste porosity and pore sizes are governed by water cement ratio, and even ITZ porosity is governed by water cement ratio. So same model, same concept can be applied, and you can arrive at same mathematics based on Griffith's fracture theory. But this is semi-empirical. The scope of improving it for concrete, there could be an improved model. This is depending upon type of aggregate. This is if it is subjected to high temperature and so on. There's a constant. And this constant is an empirical constant. So one can arrive at better mathematical model. This is semi-empirical, better mathematical model one can arrive at by doing some research. Right? Okay. This is what I talked about. But this fits in pretty well for many results. For many results, for our results or others' results, they fit in pretty well. So that's the kind of relationship one gets. This is the cement content, this degree of hydration, 1 minus 5, and the median pore radius, which again we can determine from our model. Knowing the water cement ratio and diameter of the cement particle, average diameter of the cement particle, and also by knowing the age. Elastic modulus, that's what I said. Aggregate, therefore, higher modulus aggregate will give higher strength. Compaction obviously brings in pores and creates problem. Effect of age, more hydration, less water, less pores. And this is what is Abraham's law, original. This is our mortar from the model. We get similar results. So this is what it is. Now I quickly want to come to fiber reinforced concrete, because this is another material into the cement-based material. So the mathematics can come in, mathematics are there very much, and your improvement is necessary. In both, we have seen the fresh state or moldability concepts, and also in strength. It's not empirical purely. We have made it at the semi-empirical level, but it can be made into more physics and mathematical level. Fiber reinforced concrete, that's what it does. Short, randomly oriented discrete fiber, crack arrestation property, pseudo ductility, flexural strength. Low workability, obviously they reduce workability, and this workability depends upon fiber length to diameter ratio, but they have better bleed resistance. So quickly I'll look into this. You need high cement content and low maximum size of aggregate. So this, if you put in the cement-based materials fibers, what they do is they arrest the crack. If the crack would have come because of the compressive load or tensile load or flexural load, which will generate tension, the cracks would come and the fibers will bridge the crack. And that's how they do this crack arrestation property. Now if you understand this, these models are available, fairly old, not very new. You can look into all aligned fiber composites, force, tensile force, let's say, long aligned fibers under tension, fiber and matrix have same strain. P is the sum total of the load carried by. Vm is the volume fraction of the matrix. Vm is the volume fraction of the matrix, so 1 by Vf. Vf is the volume fraction of the fiber. Therefore, modulus of elasticity, because they are now in parallel, will be something like this: Vm Em plus Vf Vf. And tensile strength will be also shown, can be shown as Vm sigma m plus, tensile stress. I am not saying strength. Strength will depend upon which fails earlier. Tensile stress would be the stress in the fiber, stress in the matrix, because elastic strain is same. So this is how it will be. But if you have short random fibers, this equation has to be modified. Right? So now the composite strength not will be sigma Vf, but with some factors, because all the fibers are not acting parallel to the load. So a fraction is acting parallel to the load. That's called orientation factor. And another full length of the fiber will not be effective. So that's called length factor, because full fiber may not be stressed up to the sigma F level, right? There's some distance required for stress transfer. We'll see that. Elastic modulus will be given by this. So fiber now will not contribute the full, but it contributes by a factors which are fraction, so is the elastic modulus for short random fiber. So these two factors are called length efficiency factor, and other one is called orientation efficiency. Length efficiency factor is less than half for length less than some critical length, and if the length is more than, then this is given by this factor. Basic theory. So continuing. Oh, I have gone to the other side. Did I go to the other side? What is this? Yeah, this is the theory anyway. Forget it. No derivation is required. This already I have told you. Right, this is the last. Yeah, this we have said. Repeated. So critical length one can find out. If stress developed is the sigma Fu ultimate, the fiber yield stress or failure stress. Length if it is small, because the friction shear, bond shear, which transfers the load. So if you are pulling from both the sides, very little bond, through the bond only the load is transferred. But if the full fiber is, the maximum stress is, possible stress at failure is reached, then it's called critical length. Like your, development length in RCC. If the length is less, you'll have less here, not sigma Fu. And if you have more length, because after that the stress will not develop, whole thing will be under sigma Fu when failure occurs. Right? Okay. So this is the length efficiency factor. Length efficiency factor is given by, if it reaches sigma Fu, then the average stress we look into. Average stress will be half LC into sigma Fu divided by LCFU if it was full. And this value is half, simply half. This value is simply half. Right? This value is equals to simply half for this. For this it will be less than half. For this will be also, or slightly, it's slightly, it may be more than half. It will be more than half. One can calculate this out. Orientation factor is for a line fiber, it is 1. In plane, if it is a 2D element, then it will be 1/3 or 1/3/8. And this is for 3D random. If the fibers are 3D random, then 2D random, another layer by layer, if you put it, it will be something like this. So critical fiber volume is that required to enhance the tensile strength of the matrix. Now, just a minute. Now, basically this comes from twice pi RLC. This is the length, right? Half tau shear stress is equals to sigma Fu pi r square. That is the LC length. LC length is this, right? So LC length is critical length is given by this formula. Critical length you can find out from this formula. If the bond shear stress transfer full load through this, so half the length of the 2 LC is the length, LC is the length, 2 half LC, and 2 pi r is the diameter through which it transfers. If this is equals to sigma Fu by pi r square, so LC is obtained from this, LC is obtained from this, and LC is equals to given by this formula. LC is given by this formula. Same as development length. So one can find out the critical fiber content conceptually. As you increase the fiber, it will increase, right? As long as both are bonded. But a point will come when matrix cracks. Sigma Fu Vf, the maximum load that the fiber can take, is given by this. And this is the point. If you put this much of as a fiber volume, it's a function of fiber volume. So if we increase the fiber volume, a point will be there where these two lines will cross. Now, beyond this point, because this is the failure of the composites, sum total, sigma mu plus sigma mu plus sigma f plus bf. So if this is more than, if this sigma fu bf is more than that, then even after the matrix has failed, this can take it, right? This can take it. This can take the load. So this is called V crit, the critical fiber content. It's very difficult to put that amount in steel fiber concrete. Sigma fu is here. So VF critical is FCA, one can find out, equate this, put this sigma fu VF, sigma mu, now sigma fu VF, from this actually you can get it, or epsilon mu if you put it, epsilon mu into EC is the sigma mu, and same strain will be there. And if that stress, that is more than sigma f at that stage is more than this sigma mu into this plus sigma corresponding, one can derive this formula. I think I'll not derive, but you can derive this. One can estimate the crack spacing also for aligned fibers. What will happen is once the crack occurs, stress will get released from the matrix. So fibers will take additional stress and it will have additional strain also. So separation would be because of additional strain and reduction in the strain in the matrix. It will be something like this. So stress will increase, which will be, one can find out how much is the increase in stress, and cracks will be more or less equally spaced. So one can derive this formula too, and it's available in Hennon's book. If number of fiber is Vf by pi r square, number of fiber for aligned fibers, right? And for short fiber, you can actually get short aligned fiber. Actually, you can get crack spacing. Also, you can derive based on some modification of this one with some factors, and crack spacing you can find out. The basic concept is that at the crack, fiber is taking all the load. Between two cracks, matrix is sharing some load, because matrix will have zero load here, but it will go on increasing because there's a bond between the fiber and the matrix, and this will be the maximum matrix strength. And fiber will release this, strain somewhat, and shared by the matrix. So one can, based on this, one can derive this formulae. Due to crack, an increase in apparent strain will be shown, and you can actually arrive at the stress strain diagram. This is the derivation of these sigmas, like alpha is a factor we are using, alpha epsilon mu by 2. And crack width you can calculate out based on this concept. Simple algebra, I don't think I'll go into that. So here there's a lot of, again, if you have fiber, there's a possibility of a lot of mathematics here. Algebra, of course, sigma cu, sigma fu, bf is the failure condition of the composite. Ultimate composite failure will be at this way. Strain at failure, one can derive an expression. It comes out to be 1 plus alpha epsilon mu, where alpha is nothing but ratios of, this is the ratio, alpha, that's alpha. So one can get them. This is a kind of stress strain diagram, right? Strain at failure. So one can actually estimate this. But real fiber behavior is something of this kind, because real fiber, you don't put all the fiber beyond critical length, and we have short fiber, then there will be pull out failure, and you can find out the pull out stresses because the tau will come into picture. So this is how it comes out. If n is the number of fiber, xd is the pull-out length, etc., etc. So one can find out. One can find out xd, where xd is the embedment length inside. So one can actually arrive at this algebra. Short fiber as the L by, the spacing actually is a function of, spacing is function of long fiber spacing to the ratio of short fiber spacing, etc., etc. One can find it. Sigma cu is given by now short fiber, there's an efficiency factor comes into picture, and multiplied by line fiber. And if you have both orientation problem, then this will be the final composite strength, provided you have put in more than the critical fiber. But you can't put in the critical fiber. Effective number of fibers, this is empirically determined. For 2D random, for 3D random, half VF by pi r square is the effective number of fiber along a given direction. Failure is usually in case of pull-out for short fiber, and it has been seen that the pull-out length is L by 4. So if you have n number of fibers, average pull-out force is tau pi dl by 4, because L by 4 is the length, which d is the diameter, and sigma is therefore for n number of fibers this will be there, right? For single fiber this is this, for n number of fiber this is the pull-out composite. N is the number of fiber per unit volume, so you can find out this unit volume you take, and sigma f bf, sigma f is tau L divided by d. So with respect to comparison, you can get it something like this. So sigma composite for 1D line, for 2D random, etc., etc., you can find out by multiplying these factors. Sigma cu for composite half BF volume of fiber tau L divided by D. So that's how we can find it, because tau is related to B sigma f BU as well. So modulus of rupture one can calculate out, and one can find it out by considering this. For this was for 100 no fiber, this is for no fiber condition. For fiber condition, modulus of rupture one can find out, because the fibers will now take some tensile stress, and this will be the neutral axis. So you can take it something like this. If it is more than critical fiber, it will be something like this. If it is less than lower strength, then it will be something like this. And some cases it will be in between like this. Ideal ductile case, ideal ductile failure. Enhanced strength is something like this. So neutral axis. Now when you have fiber, this is for no fiber scenario. Moment of resistance. When you have fiber, you can model it like this, model it like this. Just let me show first the diagram. Yes, you can model it like this. This is the sigma cu. Only some portion of the fiber is taking the load. You have some strength available at given final strain. That's the final situation. And at that point, you can find out the moment of resistance of the fiber in post one. This is assumed to be 3/4 d. If d is the complete depth, this is d by 4. Neutral axis depth typically is of this order, but it will depend. You may have to calculate it out, and one can arrive at. This is ideal. This you take this strain, this stress level, right? So idealize it like this, and then find out. So nature of the stress diagram may vary depending upon type of fiber, and you can actually idealize them. So it has been seen that moment of resistance of fiber concrete would.
You have to unmute yourself, sir. Yes, it's fine now.
Sorry. My hand just touched it. No, I'm only saying, repeat this. I'm only using a stress diagram of this kind. The crack has occurred, but this failure has not occurred. So there's some residual tensile strength in the tension zone. And this is taken to be 3/4 D. This is 1/4 D. And using this, one can calculate out the moment of resistance. This is the matrix compression strength. This is the compressive strength, tensile strength of the composite. And based on this, like you do in reinforced concrete, you can arrive at, sigma moment of resistance, something like this. So you can see that sigma Cu, you can actually compare, even if this is 42%, if it is very small, quite small, 42% of the tensile strength of concrete, still you will get enhancement. Compressive strength is given by this formula, the compressive, flexural compressive strength, because there can be failure by that. So that's the kind of mathematical derivation possible for fiber concrete, right? It's almost, people, there are a lot of theories. This is just simple, basic. But there are a lot of more fundamental works have gone in. People have modeled the composites. So fiber reinforced concrete, if you're rating fiber, mathematical tools are available, mathematical models are available, and you can go far beyond Hennon's idea. This is from Hennon's book. You can go far beyond. Now, type of matrix that you have: high strength matrix, normal strength concrete. Cement paste will be higher, around 70% paste has to be there in this kind of system. So high strength matrix is very good, high performance concrete. And fibers are something like this: the glass fibers, Kevlar fibers, boron, carbon, and some more like this. Steel, we know, is somewhere there, high tensile, high yield steel, right? This is a mild steel. Polyester, Kevlar would be there, ultra high, this glass fibers, high strength carbon, etc., etc. There can be several of them. These fibers, high density polyethylene, low modulus fiber, or polypropylene, whose modulus of elasticity is less than that of concrete, they are not structural. Or polyester, although strength is high. Strength is much higher than concrete in terms of tensile strength, much higher than steel, even mild steel. But modulus of elasticity being low, they deform more, so crack arrestation property in the hardened state is not there. But they do enhance the early stage properties. Okay, we'll come back to this sometime later on. Steel fibers have been various kind of bond to improve the bond, various kind of fiber cross sections have been used, trimmed fiber and so on. But they reduce down the plastic state property. So you can see it's measured by VV time, sometimes modified VV test. Now if you measure by VV time, it's actually very stiff. As your L by D increases, right, VV time increases with the fiber percentage. So fiber percentage is limited by L by D. Lesser L by D, you can add more fiber. VV time should be low. Supposing your VV time allowed is 30 seconds. So L by D should be 66, then you can use around this much of volumetric by volume. Mass, it will be different, because if you divide steel 7.85, so it will be much less volumetric. Is this? Because two things. Another is the aggregate. If your aggregate size is large, fiber tend to come closer. Large size aggregate, fiber tend to come closer. And they form a ball. That's called balling. So maximum size of aggregate has got a role. Therefore, paste content has to be high. MSA should be low. And about 70% should be paste. Good fiber. So actually for high performance concrete, this becomes very good, because there we use around 50% paste to control what is called differential shrinkage. Bulk shrinkage is allowed, precast elements, but differential shrinkage we control. So their fiber gives you good ductility, and it's being used actually. So fiber spacing is non-uniform if you have larger aggregate, resulting in what is called balling action. These fibers will form balls-like thing, they will form balls, and There will be voids inside. They bring down the properties and compaction becomes difficult. So MSA, this is kind of diagram people have seen. And an empirical formula is available. The maximum steel fiber you can add is given by 1 minus Ag, where Ag stands for proportion of coarse aggregate, L by D inversely proportional to. So if your proportion of coarse aggregate increases, critical fiber content for maximum fiber by mass, this by mass, you can add is this. So this has to be reduced, this has to be high. Critical fiber content, if this is high, then this will be less. Sorry, this has to be low, and so on. Plastic fiber reduces bleeding, plastic shrinkage cracks, and low density thus high volume. Actually, they form a net because their density is 0.8, sometimes less than water or similar to water. They form net. Low density forms network and resist bleeding. Will not allow water to come in even. Particles are too closer, fine small particles, paste particles. Reduce the plastic shrinkage. Well, there's a scope for modeling this. As well, the plastic behavior. There's no model for this right now. So mathematical generation is awaiting here. People have tried to model bleeding by Darcy's equation. Some by Darcy's equation, some by Stokes' law. But I don't know what can be applied here. This still didn't find so far any paper on this. So that's related to fiber. But the mathematical generalization is very much possible in durability. That's the last phase of my talk, I believe. And let us see. It is basically defined as a capability to maintain minimum performance level over a specified time. So my strength should not reduce. Shrinkage creep properties should be appropriate. Fatigue strength should be all right over a specified period of time when exposed to some environment which will cause degradation of the material. So this performance, it must fulfill its function. That means fulfill its capability to withstand the load, allow transport of vehicle, if it is a bridge, allow activity, human activity within the building safely, not like the Mumbai buildings where it is falling down every other day. And that's because of deterioration. Lot of corrosive environment, gradual decrease of performance with time. So this has to be taken care of, maintained actually, but they did not maintain. Now this is quantified in terms of service life. I don't think I'll talk of different lives here. Service life is through which it is actually controlled, right? Service life control concept, which I mentioned in the beginning. It is modeled through service life. Physical life as it remains. For example, although Konark Sun Temple is having some problem, right? I'm not talking of the 1906 problem where actually something caved in, but otherwise laterite stones are having problem from the seashore, I believe. But generally such structures will last for very long if you maintain it, right? If you maintain it. Sorry, Konark Temple, yeah, I think, yeah, it's actually, you can't get inside because it has been filled with soil, right? So service life is the quantification of durability. Let's see what is it. Damage occurred due to overloading, say earthquake damage. Fatigue damage also we talk about. Deterioration leading to serviceability limit failure. Distress occurs. This do not lead to collapse, but overloading may lead to collapse. This can lead to collapse. Anyway, so cement-based material, concrete, these are not maintenance free because you have produced them with the expense of energy, man-made material. and they will degrade with time. And a point comes when it reaches a serviceability limit. So serviceability limit means appearance of first crack. This is degradation specific. So that's serviceability limit, and this is service life. So structure would not have collapsed, but a particular element would have reached its serviceability limit because material has deteriorated. So you can have maintenance policies like this, but the best policy is something like this. And nothing should happen till my service life. But sometime unforeseen, so this can happen. Sometime unforeseen, this can happen. So you repair it and it goes, and several repairs. But the best way would be repair it in such a manner that it goes to intended design life, which is your intention. For example, 50 years for building. You know, that's what you have taken the return period of wind. Or 100 years for bridges. Or highest flood level you would have taken, some notional concepts of intended life. These are kind of degradation processes. In concrete, some of I'll take for modeling, not all, because models for all are not available. Some are more prominent, therefore people have started modeling. But one most important thing is this. All over the country, it's not coastal Orissa or coastal Goa, but even the northern Indian region, because of poor construction practices. So this is most common. Maintenance-free performance exposure during service, that's what it should do. All this requires water and oxygen ingress. And sometimes both. Moisture is the main thing. Therefore, modeling moisture ingress is very important. Water is the most important thing. And this is the major cause of our serviceability failure. Corrosion of river, that's occurs only in presence of water. This is induced by carbonation and chloride attack. This also occurs only in presence of water. Chloride ingress occurs through water. So this is what it is. Medium of water. Quite often, if it is coming from outside, if it is already there, then you have the problem right in the beginning. So water plays a major role in the evolution of degradation process in concrete. Therefore, this is most important. For exposed concrete, source is the atmosphere, humidity, rain, and rain penetration. And marine condition may bring in chloride, but that too with water again. Relatively drier location would have less sensitivity. So if you want to predict or estimate the service life, it must be based on climatic, because humidity is based on this. Precipitation is the rainfall scenario. Precipitation is the rainfall scenario. Precipitation is the rainfall scenario. Precipitation is the, other one is precipitation, and marine exposure is the other one. So we can define zones of service life prediction based on climatic condition, precipitation, and marine exposure should be separated out. Let us see how do I do it. Precipitation in India. There's a precipitation map. Dry. Highest precipitation. Highest precipitation somewhere here. Highest precipitation is somewhere here, somewhere there, somewhere here, somewhere in this zone. Highest precipitation zone is here. And this is available. With some color coding, I'm just trying to put it. Yellow is the least. Green is the maximum. Green is the maximum. Just 1 minute, I'll take.
Just wait.
Is it visible now?
No, so you have to share the screen.
No. Yeah, right. So we are back. There's a little bit of problem.
Yes.
Sorry, there's a little bit of problem. I'm also visible. Yeah. So there's a little bit of problem because there's a dog which came in and he wanted to also sit by the side of me. Right. Okay. Okay. So. Right. So coming back to the last part of it, actually, so what I was saying, this is our precipitation map. And then this is our climatic zone. So you can see that this yellow color is called warm humid zone, where the rainfall is high. This is dry but cold. This is dry but hot, desert. But I have superimposed the marine zone close to it. 10 kilometers within the marine environment will be affected. This will be somewhere there. Within 10 kilometers, this effect of marine zone is very much there. So we have these climates in the country: warm, humid, hot, dry, warm, humid, temperature, cold, composite. And and there's a zone for corrosion, marine zone also. So if you want to calculate the service life, then first I should separate out the marine zone. First I should separate out the marine zone, which is there, right? Corrosion zone, prone zone, coastal zone prone to chloride-induced corrosion. This I should separate out. Now here again, if it is submerged all the time, then the risk is relatively less. Calculation is also simpler because chloride would come through diffusion process, and concrete is saturated. Boundary conditions, of course, of the equation I'll show you. If it is a splash zone where wetting and drying occurs within high tide, low tide zones, there Chloride diffusion will occur through solution. The water will go in, leaves up chloride and come back. So you have a periodic boundary condition of wetting and drying. And on shore, 5 to 10 kilometers from the shore, chloride accumulation at the surface followed by ingress of rainwater. It is basically because of wind-driven chloride, wind-driven rain-induced velocity flux, etc., etc. So wetting, drying related to this. Non-marine zone, hot dry desert, moisture ingress induced carbonation. Corrosion of river or any other deterioration, moisture ingress is due to, due to this moisture ingress if it is there. And wind-driven rain is very important here. Warm humid climate, same moisture-induced carbonation, corrosion of river or any other deterioration, and composite monsoon climate. And there are some zones where very high precipitation occurs, like Kodaikanal. So you have most of the days it's rainy, many places, or even in northeast. So one can separate zones for service life calculation. Now, this is the most crucial one, corrosion. And this is a simplified model, very simplified model. Actually, there are more complex models are available, but for my purpose, this is good enough today. Quite often, steel doesn't start corroding right from the first day. It takes some time because there's a cover. This is your river. There is a cover. There's a clear cover. And this concrete here, it provides protection. But how does it provide protection? Concrete has got calcium hydroxide, sodium hydroxide, potassium hydroxide, which are highly alkaline, these two, and this is also partially. So this keeps the pH of the concrete to a level of 13 or so in the beginning. Now under such condition, iron, steel, Fe, it gets oxidized. It gets oxidized in the process. Maybe we'll see that to Fe, O3, Fe3, FeO or Fe2O3, Fe3O4, etc., etc. These are called black rust are not dangerous. So, I'll have maybe another slide is there where we'll see that. They are not dangerous because their density is similar to that of the steel itself, close to that. And they are thin dense layer. Do not allow more steel to get dissolved. That's called passive condition. If the chloride is coming from outside, right, if it is coming from outside, then it requires some time for chloride to penetrate through the cover. But if it's there in the ingredients, then this will be zero. Tp will be zero. After that, corrosion starts, and someday the crack will appear in the surface of the concrete, and we call it service life period has reached. First appearance of first crack. Some situation in pre-stress concrete, bar loss could be so high that there could be even failure. Right? Diameter loss. So diameter loss is another issue. Some cases it could be there. But I am looking at this at the moment, which is more common. Now, pH of concrete can be reduced by atmospheric carbon dioxide. And this is called carbonation process. Carbon dioxide concentration here is high, it's about 3-4% in the atmosphere, or maybe slightly less. Here it is 0. So by molecular diffusion, carbon dioxide can come because there's a concentration difference. And Brownian motion, particles hit each other, they will collide, and they will try to penetrate in the pores. And if there is water present, they can react with calcium hydroxide. So calcium carbonate forms. Calcium hydroxide reacts with carbon dioxide and forms calcium carbonate, and pH gets reduced from 12.5 to 9. There are a lot of intermediate reactions actually. I'm not showing that. Basic force is the osmotic pressure, right? And if I take a small dx element, at distance x where carbonation, this is already carbonated and carbonation is occurring. So dq, the quantity of carbon dioxide that is entering the flux per unit area, or in, let's say that through some area is A, will be something called diffusion coefficient. You know, this is related to Q is equals to diffusion coefficient into dc dx. That's fixed diffusion equation. So C0 minus Cc, where you know C0 is there outside, CO you can say, and Cc in the concrete, outside to concrete, divided by x is the distance, that is your dc, and x is the distance, so dc dx. So one can write it like this, one can write it like this, one can write it like this. dq is equals to dA, C0 minus Cc divided by x. And over dt time, because this is in meter square per second, so if I multiply it by time, dt time, I get this kind of an equation. And this will be neutralized by A is the amount of alkaline material which can consume carbon dioxide per unit volume. So A into dV volume, which is dx into A. And if I integrate both sides, I'll get x k root t. You know, A dx, A will cancel out. And I'll have x coming here, dt here. So some constant, it can, you know, some constant into t dt is equals to x dx. So x square by 2 into some constant, one can write that kd. So by integrating, I simply get this. So you can see that depth of carbonation is a function of root over time. Now more complex models are here, right? Let me explain this model. If pi is the porosity, W is the amount of moisture content, carbon dioxide concentration within the concrete, rate of change of carbon dioxide concentration within the concrete time, per unit time, will be given by this, because it is only the air which will absorb carbon dioxide. This volume will change. Pi is the porosity, W is the volumetric moisture content. So that's the space available where carbon dioxide is. Minus whatever has come from outside, right? So this is the space in which it has come. dC is the diffusion coefficient. This is the concentration of carbon dioxide minus 0. Outside carbon dioxide, you know, this is the rate of change of carbon dioxide concentration in space over a small space dx. This is the change in the carbon dioxide concentration. Somewhere it is 0, somewhere the carbon dioxide concentration is there. And this is the space available. Now, whatever is coming in minus whatever is going out in a small volume, dV volume, or dx along this direction, dA along this direction, let me call it. Small area will cancel out from outside. So whatever is coming in minus whatever is going out is given by this formula. This is what is coming in minus whatever is going out, one can actually find out, I mean, any mass balance equation. And this is what is consumed in the system, reacting in the system, a sink term. So it's a sink factor which is reacting. So this is how the rate of change of carbon dioxide concentration within the concrete will be given by this formula, right? Now you can solve this for appropriate boundary condition. So W is a necessity. I need W, moisture content. I got to know W. That's one. I got to know it. Now if W is 0, this reaction will not continue. Sink will be 0. No reduction. Right? And in fact, differential delta, this term also tend to go to 0. Okay, so that's what it is. So W has to be there. There has to be W, a conducive condition for reactions. So moisture ingress in concrete is a necessary element. And carbonation can occur in our climatic condition if you look at it. Since it doesn't remain wet all the time or moist all the time conducively, some time of the year it is dry, sometime it is wet. Now if we consider a total wet situation, saturated, this is the moisture, critical moisture line, beyond which, 50 to 40, around 45 to 65% relative humidity. 45 to 65% relative humidity when carbonation occurs. And corresponding moisture content we can calculate using Kelvin's equations, which I will show later on. So there's a conducive moisture content. If it is fully saturation, carbonation will not occur. If it is fully dry, carbonation will not occur. So if it is fully saturated and it is tending to become dry, this is the critical moisture line, then carbonation will occur. But suddenly the rain comes, saturation increases, then carbonation will stop and it will fall like this. So it's actually a periodic situation. If it is, drying occurs, carbonation occurs, then stops. Again, next phase, next year, and next year. Every year it occurs in that manner. Right? Every year it occurs in that manner. So carbonation, I need to model this. If I want to do this, I go to model this. We'll look at the model possibility. If you look at chloride ingress, in saturated concrete, high concentration of chloride here, no chloride here. So chloride actually will come by same fixed diffusion equation. Sorry. Ulta. Basically, electric potential is a driving force because high charges, more charges here, more charges here, more charges, chloride ion here, more charges, less charges there. So driving potential will be electrical, but it can be actually written again in the form of fixed diffusion equation. It can be derived. So this is chloride diffusion equation constant. And again, same mass balance equation. So rate of change of chloride with time at a given small element would be whatever is coming out in minus going out from the small element. So this term is nothing but whatever is coming in. This is a flux coming in dq. This is actually dq. dq is a flux, change in flux. So dq, it can be written as dq dx is equals to dcl. Rate of change of flux coming in minus coming out over the distance of dx. So mass balance equation actually. So it's also a second order partial differential equation, parabolic type. And some people use D independent of x and concentration. But truly speaking, it is not so. We find that it is not so. Majority of the models that has been used, or you find software, they will be using D as independent of concentration. This is not correct. But at the moment, this is the model available. And if it is taken out, then this becomes the equation. So solution of linear fixed diffusion equation for the boundary condition. This boundary condition solution is available for thick wall, but this is not the real life situation. This is there in most of the softwares and models. This is wrong. In Indian condition, this is not valid. For this, the boundary condition will be at t less than 0, C at all x, and at t less than 0, concentration is constant. At t is equals to 0 or greater than 0, at x equals to 0, this diagram will show you at x equals to 0, this phase, in x increasing along this direction, C is equals to Cs, that remains constant. So suddenly I raise the temperature flux of the concentration of the chloride at the boundary at Cs and keep it there. And at infinity, again it remains C0. So it's semi-infinite medium. And we can derive this using what is called Boltzmann transformation. This is available in heat transfer books or otherwise. So Boltzmann transformation is a new variable is written in terms of this, and this equation, parabolic equation, is converted into parabolic equation is converted into parabolic equation is converted into partial differential equation. Parabolic partial differential equation is converted into simply ordinary differential equation, which is solved, and you get the solution, closed form solution, in terms of error function. This is not valid for most of the Indian situation, but this is valid for certain situation. In, for example, submerged condition might be where the concrete has been constructed and moist, seawater has been allowed to submerge. So submerged pier, this may be available as long as your D is constant. If the D is varying, this equation also will not be varying. But the other problem comes, what is the CS value? So they assume a CS value makes life complicated. I think reality, maybe, it's not validated also much because it's a long-term validation. So anyway, the validation is also other factor. Mathematics is coming, but validation is very important in this one. Error function is defined like this: e to the power u square dt. Because you can't evaluate this, you can see this similar to normal distribution. 2 over root pi. You would have seen normal distribution, right? Gaussian. So this Gauss's error function. So something similar. So error function complementary is used, and one can derive this formula. One can derive this formula for service life by some approximation. If I know the threshold chloride, the time required to reach the threshold chloride, I can find out, and this is the equation. So you see this from error function solution. But as I said, this is not valid for most of the cases. But this is there in the book by Bhattacharjee. This is there. A software called Life 365. They were using this, but I think they might have changed. But most often, this is the most commonly used, or some form of this is used. But often ingress is in partially saturated concrete, like splash zone, or offshore, slightly off. Not on the. In the shore, onshore, not offshore. Onshore within 10 kilometers. Rain will penetrate this. Now, in that case, diffusion occurs, but chloride also goes with the solution. And the equation becomes far more complex. Rate of change of chloride now, there's some chloride binding. Earlier one did not take chloride binding because some of the cement components, cement hydrates binds, illuminate. C3A hydrates 6H. It binds chloride, reacts with chloride, and captures some of those chloride, chemically combine them, and it is not available for deteriorating the concrete or allowing corrosion process to progress. So one can have this kind of an equation model and solve them for appropriate boundary condition. You'll have two terms. One term is related to change in the chloride with time. One term is the solution, another with the concentration. So this is with the solution, this is the concentration, I think this is a porosity term, and so on. So there are more complex equations, as I said, and all require moisture index. Now so we thought that first thing targeted should be moisture, in just wetting and drying. And since India has got a large area of rainwater penetration, situation exposed concrete, bridges and things like that, so one should look into the moisture index. Usually driving force is capillary suction, and Richard's equation is followed. Same diffusion equation. Only thing you have now, Richard's equation is this. This is moisture content dependent. This is degree of saturation or relative moisture content. I don't think I'll go too much into this. This is called hydraulic diffusivity. Any derivation or anything. And boundary condition for rain penetration is given by this, where this is wind velocity, this rainfall intensity. And rainwater comes in, saturates the surface, and then by capillary action water goes in. Surface is a flux, and you have wetting and drying cycle. Rainy season, wetting will occur. Drying season, which could be very long, depends. And degradation period would depend upon how long the conducive moisture condition is. So one has to actually estimate them for Indian scenario. While drying occurs, there is something called constant rate drying, then falling rate drying. Let me explain them. Constant rate drying occurs only from the surface. This is inert zone, and liquid comes into the surface, evaporates. Evaporation front. And this is falling rate when the evaporation zone has receded. Here there will be heat transfer through this. Outside temperature is high, this is called wet bulb temperature, dry bulb temperature outside is high, and evaporation takes place. Relative humidity is low. So all this has to come into the model, and this comes into the model. Diffusivity, there is a problem. Drying diffusivity is taken like this. Wetting diffusivity in some cases is taken like this, where D0 is the diffusion coefficient in air. And this sort of exponential equations are there. Flow through porous media, those people who work in soil, they use something similar. The Richards equation is very much used by them. Now we try to get permeability from pore size distribution, and there are some complex models on like this. How did I arrive at? I'm not going to discuss. It will be very difficult at the moment. But from pore size distribution, one can arrive at hydraulic diffusivity. This is the same mean distribution radius. D is called dispersion coefficient. M is an empirical constant, and surface tension of water, viscosity, and all that comes in. This we can obtain because this equation I have shown you earlier. So with that we can arrive at this. And for a given relative humidity, I can find out the size of the pore at which moisture would be there, liquid water will be there from Kelvin's equation. This Kelvin's equation. So if the relative humidity is this, temperature, absolute temperature is this, R is the universal gas constant, this is the radius in which condensation will occur, this surface tension occurs. So Kelvin's equation, etc., etc. So moisture content can be obtained from R. So if we know the temperature, if you know the relative humidity, I can find out the radius at which condensation will occur and volume of the moisture. And dVdr, if the pore size distribution is known, from R1 to R2, from given R2, 0 R2, lowest R2, current R, I can find out what is the degree of saturation. So based on this, actually, we did some analysis, and we found out the conducive days for carbonation. Based on this statistical treatment of the climatic data, rainfall data, etc., etc. And how many days actually there will be a situation, distribution of diurnal rainfall distribution, etc. I am not going to this. Wind-driven rainfall, their distribution. So based on some statistics as well, and Kelvin's equation, theta is this. So we could find out upper limit of the moisture, because 65% carbonation occurs at 65%, beyond 65% porosity, carbonation will occur, or corrosion will not occur below 90% relative humidity. So upper limit and lower limit for each temperature we can find out. For 60% relative humidity or any other relative humidity. And such conducive moisture condition but each climatic zone or each station in a climatic zone one can obtain for various water cement ratios. And you can get the carbonation depth. For carbonation depth 100, non-conducive days actually is much higher, right? Sorry, conducive days for uh, carbonation is much higher with 0.6 water cement ratio, 0.5 if you provide 100. So in fact, actually you can obtain the cover depth. If you provide cover depth up to let's say 50 in water cement ratio 0.6, then you have a problem. But if you provide 0.5 water cement ratio, 162 days carbonation will occur. 0.4 no days carbonation. This is in Jodhpur, but in Kodaikanal again you can find out and so on. So one can obtain this for corrosion, one can obtain this for various climatic. So cover depth for high water cement ratio. In hot dry climate, this is Jodhpur. That's again obtained. So if your cover depth increases, water cement ratio is 0.6, number of conducive days where corrosion would occur, full year it is not going to occur. Only some part of the year it will occur. Similar results for other cities actually has been worked out, some of them. And that's it. And this is some of the moisture distribution results. I don't think I'm going to from finite element from modeling and all that. Carbonation I've already told you. Chloride, this is actually got repeated. I don't think I'm going to go through this, but let me come to the end of this. Chloride binding is also taken into rebar corrosion process. This is what I wanted to tell. This is an electrochemical process. Last part, absolutely last. This is another modeling. Now, this is typical corrosion process in steel in concrete. Some part of the concrete actually acts as anode, some as cathode. At cathode, electron comes out, at anode, metal dissolves. It reacts with oxygen and water, hydroxyl ion forms, and this is formed. Now, this is not stable and breaks down. It can break down into Fe3, FeO, or Fe2O3, or Fe3OH at high pH. Fe3O4. FeO, Fe2O3, Fe3O4 at high pH. Then I have no problem. But at low pH, it forms red rust. So volume expansion. Now what is red rust? What is red rust? What is red rust? Red rust is FeOOH H2O. If you rewrite it, it will be something like FeOH3. It's a form of FeOH3, red rust. And that's what is problematic. That's what is problematic. That's what is problematic. So, as you can see, FeOH3 occupies maximum volume, relative volume. FeO is this much, Fe3O4. This is unstable, these are unstable. If the pH is low, it can go to this. If chloride is high, it can go to this. And that's why high pH carbonation, post-carbonation high pH creates problem. High chloride, this creates problem. And what happens? This is what will happen. The expansion will occur. Initially, rust product will form. Then it will start exerting pressure and cracks will come. Now this can be modeled through fracture. And this is service life I have already shown the last. So people initially tried with thick cylinder and thin cylinder type. Average of thick and thin cylinder. ZP Bazan did this kind of work long back 79. And FEM models some tried. Right? This is how it is. Corrosion products would form. Exert pressure. And if you consider it to be thick cylinder and thin cylinder, thick cylinder and thin cylinder, take average of this. Right? So you can assume there's a hole and the pressure is exerted. And this is one of the cylinder boundary. These are the kind of work that has been there long back, 2009. And cracking surrounded was, so you can do this by smeared crack approach. Those who are structural engineers, a good problem for them. We try to do something, a little bit compressive behavior of concrete, tensile, etc., etc. All these properties we need. Domingo et al.'s model stress strain behavior of concrete. We try to model through this. Tensile behavior by CEV FIP model 1990. And failure ratios of concrete to define concrete smear crack model. Fracture, and ratio of ultimate biaxial, etc., etc. Some of those assumptions that we made. Major problem is validating this through actual results. Maximum results, simulated results are available for 4 years, but actually it takes much longer time. So if somebody does, so we did some finite element, 2D element modeling, 8 node, plane strain condition, nonlinear finite element analysis we had to do. Scheme of nonlinear analysis, different approaches, right? Pressure through the periphery, applying uniform ideal radial displacement, the 2 cases. And these were some of the results. Concrete cover cracking time. So for various rebar dia, concrete strength, middle bar, center corner bar, individual bar, we try to look into. For different C by D ratio, C is the cover to diameter ratio, and critical pressure required for concrete cover cracking we could obtain. Concrete cover cracking increases in C by D ratio, etc., etc. Modeling is possible, but validating is important. Critical radial displacement for bar also one could obtain. And then modeling of rust, you assume uniform all over the place. People have tried something of this kind, varieties of. So you can do service life prediction then, when crack will come. First, do the chloride modeling if required, carbonation modeling, and wetting and drying modeling. So, in absence of mathematical generalization, it's not generation, generalization, largely empirical and engineering judgment oriented at the moment. But I think we got to look into this. Both mechanics and physical chemistry, physics, there is a difficulty. Appropriate cover for the service-free maintenance life, one can find out. And you can vary it depending upon the situation. Of course, the cost is an issue. Because precast element, if you have, you can think of, or whatever it could be thought of. So there is need to relook into this prescriptive guidelines of durability at the moment, which is there, which is highly. Modeling service life needs consideration. First thing is wetting and drying, an Indian scenario that we have proposed. Conducive days can be estimated. Appropriate cover for given water simulation will be determined through parametric study. I think that concludes my discussion. This is the difficulty, complexity, and thank you very much. So if you have some questions, I'd like to answer. And that's it.
Thank you. Thank you very much for your presentations. You have so energy that a long time, and you did not hesitate single time. Thank you. I will ask our participant to ask some questions. If you have any queries, you can clear your doubt, because in the concrete many people are working, and if you have any doubt you can ask. So I get one query is actually Srinandan Sahu, probably you know him. Srinandan Sahu. Srinandan Sahu. Srinandan, long back probably he contacted you regarding some concrete and some queries. He asked that how to increase the pozzolanic activity of mineral admixture based on concrete without using thermal curing. How to increase the pozzolanic activity in mineral admixture based on concrete without using thermal curing. So basically he's asking how to increase the pozzolanic activity.
I got it, what he's saying. Now, obviously there are physical ways of, grinding them.
Okay.
Right? Or using fine ones, but that's not the best way. I think what he perhaps wants to know is there an accelerator,
Yeah.
chemical accelerator, which will increase the pozzolenicity, or rate of reaction of the
Yeah.
pozzolanic.
Material.
I have not really come across an accelerator which enhances the pozzolanic reaction very much. I mean, chemical accelerator which enhances it very much. But mm, uh, there are, of course, no, there are admixtures at the fly ash plant level to improve the fly ash. No, I have not come across one. But essentially the dissolution of it is the dissolution of production of calcium hydroxide first of all. So one way could be if you use a cement which is relatively fast hardening, rapid hardening, or 53 grade with the pozzolana, maybe this will show better results because you should have sufficient calcium hydroxide, number one, and dissolution of this product. So supposing you have come across inside, both would be difficult. It would be difficult. I do not know a chemical admixture which does this job. Not really.
Okay.
Um, plasticizer will improve a little bit, but not much. No, I have no idea. Not really looked into.
Okay. So one more query is in your during lecture you told the Konark temple is filled with soil inside. So I was
Sorry?
curious. You just some and then in your lecture you told that the Konark temple, that Konark temple is filled with soil in the inside.
Which temple is being built?
Konark.
Konark temple. Oh,
Konark.
acha, no, no. Konark temple actually it collapsed. No, I think
Yes.
you know it. The
Yeah, I
people.
visited. Yes, I visited.
Yeah, yeah.
I have.
It in the beginning of 20th century, it actually collapsed. But
Okay.
right, basically because I mean, there are reasons. I think the CBRI was trying to look into that investigation also, and there are a lot of conferences. I had the chance to visit one of them, one of the
Okay.
conferences, but nothing specific there. They're not. It's not easy to take out that. I mean, they're not able to come out with a solution.
Okay.
Basically, perhaps there's somewhere I read. I'm not remembering why did it collapse. But during those first they saw some part of the collapse, and then they thought that whole thing will collapse, so therefore they put in soil inside. So by putting
Oh,
soil inside, they are actually stabilized it, so that and you don't go inside, you move from outside only.
yes. Yes. Yes.
But there is a problem of laterite soil being attacked by seawater.
Okay.
Some of them are actually degrading. In fact, I suggested the Archaeological Survey of India that we can
Mm-hmm.
look into if they give us some sample.
Okay.
We'll actually simulate the seawater and see how it is deteriorating. Do
Mm-hmm.
wetting, drying, that the kind of situation that goes in. That's also a problem, but that did not cause the collapse. Collapse was I think there was some structural problem. I read somewhere, I don't remember that because at the moment people are only guessing what could have happened.
Okay.
And CBRI is trying to do some models, some finite element modeling and all that people try to do. So
Okay.
uh, the Archaeological Survey of India, they have a lot of historians and other people.
Yes.
They are not interested in the technical side too much, really. But
Yes.
people there, local people
Yeah.
in the state, they are very
Mm-hmm.
much interested in the temple and they want its revival.
Yeah.
So,
Because
yes, but then
tourist and all the things
Archaeological
are
Survey
there.
of India, if they would have given me sample, I could have tested and said, but
Mm-hmm.
know, perhaps the lateritic soil is not exactly close to the sea. They might have got it away, like the sea must have, seashore or sea wind must be coming in close now. Something
Yeah.
is happening. But it was an observation that lateritic, some of those lateritic stones are getting affected by marine environment.
Main environment. Okay. Okay. So I am not getting any queries. I just want to ask one and two questions related to the
I
corrosion.
tried to induce one thing to my friends actually,
Yes.
whoever are there. Please, if you are doing material research, do not think that it is breaking and making.
Yes.
It's anything.
Yeah. Yes.
Do not treat the material, mistreat the material. There's physics and mathematics behind it.
Yes.
Also,
Yes.
there
Yes.
is a science. Use the
Yes.
science. The concrete research is science oriented, and that's what I'm trying to infuse on people. That
Yes.
do not simply take it as a
Yes. Yes.
something you mix anything. Somebody other day said that I mixed cow dung to the concrete. I was very upset. That why the hell do you have to mix cow dung to concrete?
Mm,
Because cow dung itself is a very good material for its own. It is used as a manure. It is used as a kind of a fuel.
mm.
It can be used. Why you want to make that poor material, poor concrete? Why do you want to? And what advantage you are getting? So just
Yeah.
mix something and try to test and
Yes. Yeah. And that's one of the
so
research
that
way.
my suggestion will be if you're doing, and you also can model them.
At least you try to get some empirical equation that you can
Empirical and now science based also, but
science
it's
based.
complex. It's not easy.
Yeah.
Not that the theory of elasticity is well developed. That's why it
Yes.
can be applied to structural system with assumptions.
Yes.
Then assumptions that like there's nothing like simply supported beam in concrete.
Mm.
You'll have always some horizontal stresses,
Obviously.
but you model it
Model.
and make it safe. Conservative design you can do. If I want continuity, then obviously, put some additional reinforcement, that kind of thing.
Yeah.
So modeling it actually,
Yeah.
modeling it. So modeling theory of elasticity is well developed, assuming that everything is linear elastic, it is easy. Now inelastic, non-linear has also come. So
Come.
this
Yeah.
is the situation. But this modeling, this is very difficult.
Yeah.
Material will be very, very difficult
Model. Yeah.
in continuous material like this. So, but this challenge is there. You can do that research.
And
You
also
had
one
a,
more thing.
you
One
had
more.
a question.
Now I have question is related to the corrosion. Suppose we have steel bridge and that also used to get corroded, and there is a corrosion in the reinforcement bar in the concrete. So basically, what type of instrument is very suitable for testing and getting that idea that how much is corrosion occur in the reinforcement in the concrete, and what should the suitable instrument for getting that corrosion level in the reinforced steel, basically steel bridges.
See, steel bridges, of course, is exposed.
Yes.
So you can visually see and measure them simply.
Okay.
Dimensions, dimensions.
Dimension. Yes. Yes.
So clean it up and measure the
Okay.
dimensions. Now,
Okay.
there are currently there are of course magnetic imaging technique to non-destructively determine the corrosion,
Okay. For
right?
steel bridges.
But I was told as offered by somebody. He says 35 lakhs, couple of years back.
Okay.
Okay,
Okay.
so there's magnetic resonant imaging or whatever it is. But
Mm-hmm.
the other way, the way we were doing many a times over many years, would
Mm-hmm.
take some samples from uncorroded area
Okay.
and take small samples from
Corroded
corroded
area.
area.
Okay.
Cleaning to it, there are two types of solution: hexamethylamine. They are cleaning solution after cutting them out, taking
Mm-hmm.
samples, flood them, clean the rust, measure the residual diameter,
Okay.
and that's the gravimetric way of doing, or what is called Clark solution.
Got yeah.
Clark solution. So you can clean with Clark solution on hexamethylamine. Uh, Professor Bulu Pradhan's paper that has got that kind of cleaning chemicals reference. IIT Guwahati
Okay.
has Professor my
Yes.
student.
Yes. Blue Pradhan is there. Yes,
Yeah,
I know.
Bulu Pradhan. He's from Ganjam, Orissa.
Mm-hmm. And for the reinforced concrete, because reinforced concrete is already inbuilt in that embedded in that concrete, so it is very difficult to take it out.
No, you have to you see. You can first you have to do assess procedure. You cannot do it like that. If you don't see
Yeah.
any crack, if you don't see any crack,
Yes.
if you don't see any crack, then what you do is you essentially do half cell potential testing to
Okay.
find out the risk of corrosion. But this gives you some idea.
Mm-hmm.
You can measure the rate of corrosion by there are many various instruments now,
Okay.
both for half cell as well as for corrosion rate. So
Mm-hmm.
there are linear polarization technique, there are LPR, AC field instrument. There are many companies, Galba Pulse. There are
Mm-hmm.
several instrument companies who are selling the rate as well as half cell potential, also
Mm-hmm.
resistivity measurement. So you measure all
Okay.
those, find out that those areas where risk is maximum.
Maximum.
Isolate that area.
Okay.
Take least number of samples
Mm.
because you'll be damaging them anyway.
Yes, yes,
You
yes.
have to put them back again, new ones. And you can't put a different steel. You like to put the similar kind of steel.
Yeah, yeah.
Otherwise, you have to treat the other steels so that
Mm.
galvanic corrosion doesn't occur. So
Mm-hmm.
there's a complete, complete survey has to be done. So that's how it's done actually. That's how it is done.
Okay.
This
So,
total complete procedure, comprehensive procedure.
yes, yes. Now, suppose if one building is there and it is corroded, and if anybody want to rehabilitate that structure, because you can think of it as important structure, bridge pile or bridge fire, you can say, it is corroded inside, and anybody want to rehabilitate. So, is it possible to rehabilitate because inside there will be corrosion, and
Yeah,
then
yeah.
and which
It is possible depending upon the. For example, normally the corrosion would occur at places where wetting and drying occurs.
occur? Yes,
If it is submerged, chances are less because oxygen will not be available.
not there. Yes,
So visibility will be there. You will be able to see that.
okay,
Now, whether corrosion is occurring or not, periodic inspection is important.
important.
Visual and sometimes instrumental, depending
Instrument.
upon importance of the structure.
Okay.
For example, it is a thermal power plant generating electricity,
Mm-hmm.
which might actually bring darkness to many places. You can't risk that.
Mm-hmm.
So those, or a bridge which is connecting very important cities.
Mm.
So you have more frequent inspection. These are
Yes.
guidelines are available in
Okay.
certain, CIBS guidelines. I mean, no,
Okay.
might be European, but CEP guidelines. It's
CEP.
available
Okay.
actually. So either 6 years or 2 years, every 2 years, every 4 years,
Yes.
every
Yes.
6 years or every 10 years, depending upon importance of structure and where it is
Yes.
exposed.
Okay.
So if you inspect it visually once, next cycle you'll do instrumental. That means you'll check the
Okay.
upside potential, etc., etc. And if
Mm-hmm.
it's still showing the risk of corrosion low, you are happy. But if it's
Okay.
high, then you would like to do more tests.
Noted. Yeah.
That's the kind of thing, right?
Yes. Okay. Okay. So thank you, sir. Thank you for your times because you devoted so many times, and today's is long session, and I surprised that you have still that much energy to continue 3 hours continuous lecture because our participant exhausted, but you still have the energy.
No, in live, of course, you get a break. Here, there is no break, except for the dog that came in.
Yes, yes. No, that's okay. So sometimes entertaining is required.
Okay,
That's
okay, okay then. Right. Best of luck.
okay,
Enjoy
sir.
yourself.
Thank you, sir.
Thank you
Okay,
very
thank.
much.
Okay, okay, sir.
Okay, I'm leaving. Right.